is very appropriate that this cool mix of Balatros theme, which I need to turn down a little bit more, actually, at least me and my ears. This cool mix of Balatros theme by ISRG33 on YouTube starts playing right now, because this is a very good track to encapsulate my current mood. I would love to be floating along in a trance at the moment, because you know what stupid me did? Stupid me said, boy, it would be a really good idea to make my chemistry react stream on a day after I spend 8.5 hours listening to a seminar at work on high vacuum systems and physical/chemical applications of high vacuum systems in regards to depositing thin films of material on objects. It was a cool seminar. I got to learn stuff that I kind of had passing familiarity with and now have upgraded to moderate familiarity with. But, you know, in hindsight, going from a day where you listen to a guy lecture for 8.5 hours with a couple breaks in between, and following that up with reacting to chemistry videos for at least 2 hours, maybe 2.5 or so, maybe not the wisest choice I have ever made. It's perhaps just a bit draining on the psyche. I was seriously tempted today to just kind of announce, hey, I'm actually delaying the stream by 30 minutes because I would in fact like to maybe sit back and watch other stuff first. Apparently, because of the seminar today, I missed the fact that Pink Kitty Rose live streamed a whole bunch of Mega Man Buster Only today. I'm going back and watching her VOD, of course, but you know, that's the thing that I would have been like, hey, I would like to watch maybe 30 more minutes of this before I actually hop on stream and learn more shit. Because I don't, you know, I'm a little bit learned out, but at the same time, I guess now is a little different, because tonight I get to actually, instead of just being lectured, I get to also maybe teach at the same time, if I have anything to say about this, you know, that is. I'm not sure I can compete with the kind of guy who can actually identify the Coca-Cola recipe in reverse engineer the Coca-Cola recipe. I don't think there's much room to criticize his methods if he's right about it, but you know, you never know. I am excited at least to kind of actually properly clear out the backlog of shorter videos in the Chemistry Watch Later playlist tonight. Because, yeah, I maybe have milked some of these thumbnails and not actually reacted to them for a little bit too long. The intention was never to milk them. It's just that, like, a 30-minute Nile Red video somehow turns into me reacting to it for, like, an hour and 10 minutes because there's so many things I can yell at Nile about. But, I think tonight's video should be a little bit shorter. I mean, none of them are over 20 minutes. We're starting off with one that's like 10 minutes. We're going to start off, in fact, with the one that has been in the thumbnails, I think, the longest without me actually reacting to it. And that would be... That's weird. Why did... You know, I didn't pause the music there just then. The music paused itself. And YouTube isn't even showing that it's paused. So I guess that's a really excellent sign that I should move on. Stop waffling. That's not the right one. Force of habit. Clicked on the wrong layout. And just get reacting. So, yeah, tonight we are going to be reacting, or starting off tonight's reaction by looking at a video by Periodic Videos. A couple of time heavy hitter on this channel. They are educational. Well, of course they're educational. They are a group out of Oxford. They're a bunch of actual professors and one guy with a camera who likes recording multiple of the professors at Oxford for different subjects. And they teach various little chemistry things, and they're mostly geared at a introductory audience, so you don't need to know too much to actually get into what they're talking about. But thankfully, I know even more, and it's like, oh, cool. This is still fun for me to review my basics because I'm such a chemistry nerd. Today is going to be their video on dysprosium. I would press the like button if I could, but it seems to be broken. Good job, YouTube. Can't you have to spend so much time clamping down on people who play 5 seconds of a licensed song, and you can't get your own website to function. Anyway, dysprosium, as you can kind of see on the thumbnail here, is one of the rare earth metals of the periodic table. I'm guessing they're probably going to explain in the video because it comes with the territory, but a rare earth metal is sort of a misnomer. The rare earths are, in fact, only kind of uncommon in soil and Earth's crust and the mines and such. It's just that they were named so because the rare earths were not easy to process several decades ago. It was hard to separate them out from each other, and it's still fairly hard to separate them out from each other because their chemistry is so similar, which I'll get into a little bit as the video actually starts to get into it as well. But I don't really know too much about dysprosium other than the fact that it is in fact a metal that exists. It is one of the rare earths, and it has an atomic mass or atomic number of 66. Yeah, so I would like to learn more about dysprosium myself. This is one of like the cooler things on this channel. I think that they have a video on every element in the periodic table. Now, some of them were recorded a long time ago, like the old dysprosium video. That's why they have dysprosium parentheses new here. And, you know, they had less production quality, they were a little bit less interesting, and they often had less to say about the elements because there were fewer people who knew them as a household name and were able to be like, oh, hi, hello, I actually work with dysprosium for a living. I can tell you all about it. But I think it's really cool. It's like, oh wow, there's a story to tell about just about every element, except for the ones that exist for maybe like, 5 attoseconds and then disappear. Hey Scorebar, welcome. Dysprosium will now be forever ingrained into my mind. Yes, I said it like 15 times, so it probably ingrained in there pretty well. All right, let's get this rambly mess over and actually get started on watching the video. Hey YouTube, that was a sign for your UI to start working. Do I have to refresh the page? Okay, I guess YouTube just had a complete shit itself moment.
16 years ago, we made our first video about dysprosium.
You can see we've got a very thin foil sample of dysprosium.
It was rather a boring element then, and it's really gone up in the popularity scale.
Dysprosium stonks.
It's now become really quite important technologically.
Take that, lead
and
stonks.
Also in fundamental science. In the original video, Pete found a small sample of dysprosium sheet in a drawer in our store downstairs.
I don't know, it doesn't really look
wonderful
stable enough to call a sheet. Maybe call it a foil.
So and I went down to look for
crinkle that in your hand.
Pete had got. It was gone. Someone must have taken it for their experiment without admitting it because it's quite expensive metal. Fortunately, our friend Anthony Lippman and his collaborators.
So in a sense, I don't know if I, as a chemist and as a safety person, I should be upset that somebody went ahead and stole and used a 50-year-old sample of dysprosium, or happy and proud that they used a 50-year-old sample of dysprosium. Upset because it is probably not high quality anymore and it's oxidized and, whatever other contaminants have gotten to it in 50 years, so it's probably a crappy reactant. But also a little proud because it means that someone said, hey, you know what, I don't want old shit just accumulating for no good reason. Granted, it's not like dysprosium is going to get hazardous if it gets, too old, but, there's pros and cons. There's a little bit of column A, a little bit of column B to the feelings.
In the company G. Chapman have provided us with 2 really nice samples in fact 3, 2 pieces of metal and also a lump of so-called dendritic dysprosium metal, where it is crystallized in a sort of fibrous form which looks really good, and it was too nice to try and destroy chemically.
For anyone who doesn't know the word dendrite, you most commonly hear it when referring to battery chemistry. Well, if anybody ever refers to battery chemistry. Because in lithium-ion batteries, as the battery ages and gets older, the lithium ions accidentally start to, like, gather electrons and not redeposit where they should. And so a dendrite is basically a long, kind of thread-like shape for a kind of metal to end up taking on. So that hunk of metal being called dendritic makes sense. It's full of, it looks like it's made out of a bunch of thin fibers. Yeah, that's the word of the day. I love using dendrite. I don't know. I don't get to use it very often, but it's a very elegant word to basically just say a thread of material.
So I'm going to keep it to display.
Yeah, look at that metal powder burn.
We're going to show you some really
fireworks.
quite nice reactions
Literally.
to metal. But before that, we're going to talk about its magnetic properties. Dysprosium is one of the so-called rare earth elements, and it's in the periodic table above californium, the very radioactive element. But surprisingly, it's attracted to magnets really quite strongly. Neil has a very powerful small magnet.
I wouldn't know if I would call it surprising.
He managed to lift up
They're going to talk about
the larger lump of dysprosium right
Perhaps
off
not.
the table.
Hold on. Alright, so he's just going to get the filings off now. Let me look back at that periodic table they have there. So, dysprosium being, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 down the F block, so that would be then a, hold on. I want to talk about the electron configuration, so that way I can actually talk about the magnetism a little bit, because it really shouldn't be too surprising that dysprosium is a ferromagnetic material. 3D1 question mark? I don't remember quite right if that is a regular or not. And then, wait, no, that can't be 3D. Can it? Oh, wait a minute. I'm sorry, it fooled me because in, like, the second afterwards, it's like, yeah, it grouped all of these as the rare earths for a second, and I'm like, wait a minute, that's not how the periodic table wraps around it. Despite what this grouping looks like and how I explained earlier, rare earths are just hard to separate from each other because they all have, like, common chemistry. If you notice the numbers here, cerium 58 actually comes after lanthanum 57, and so, like, that's actually where the electron configuration picks up. So this is not quite right. Let me erase these numbers here for a second. I almost made the cardinal chemistry mistake of writing a writing in a 2f orbital. Good God, that doesn't exist at all. Okay, so counting down the rows here, the earliest gas is xenon. So xenon is the one that comes before these. So this bracketing is just saying that these are all the electrons that come on the completed shell in xenon. Then you have the 2 electrons in the s orbital for cesium and barium. That is row 6, so that's a 6s orbital. Then we have the 1 electron from lanthanum in a d? No, I don't think that's in a d orbital then. Because, hold on, because there's 58, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Right, so that, okay, no, that has a d. All right, going 1 energy level down is a d orbital. Reasons why are beyond the scope of this this course. And then, again, going another row lower for 4f. Again, reasons why a little bit beyond. But But this is the electron configuration of dysprosium then. This is saying that there are core electrons that correspond to what would be in xenon, so that way I don't have to write out every single orbital full of electrons going up to this point. Then the valence electrons, being the ones that are at the highest energy, and being filled in as the atomic number gets greater on the periodic table. You have two electrons on the two electrons in the 6s orbital level, 1 electron on the 5d orbital level, 9 in the 4f orbital level. The number is meant to indicate what's known as the principal energy level, which is kind of like the tier of energy that a orbital is supposed to occupy. And the letter is meant to indicate the shape of that orbital. Now, the shape of the orbital also influences the total energy that an orbital has. So, even though this is in the F orbital is in the 4th tier of energy, the F orbital is, well, many F orbitals are these weird, like, 6-lobed configurations. I can't even draw them well. In chemistry, you stop being able to draw orbitals well after the d orbitals. But you can kind of imagine, I'm going to draw this really poorly, but you can kind of imagine, like, a cube of, like, lobes that are each pointing to, like, a different corner of a cube. And they kind of alternate in shading. So, like, this one in the back, this one is, like, to the one of the upper corners. And there's a couple of different shapes of F orbital. But because basically the shape is so wacky and complex, that causes quantum mechanical energy bullshit, TM. And that causes these 4F orbitals to be high in energy, and higher in energy than the 6S orbitals, even though they're, like, deep in the atom. And so, give me a second here. I've decided I would actually, in fact, like music. Open that in a new tab. I would like to pull up my background stream. Hey there, Bear. Come on. All right, we'll pull up the Balatro theme again because I didn't get to fully play anyhow. All right. So, to draw kind of out the electrons of all this, and again, I'm doing all of this to kind of say why I don't think it's very surprising that dysprosium is ferromagnetic. A very rough electron diagram for the atoms of dysprosium would look something like this, where you have your 6s orbital down here. You then have your 5d orbital populated kind of as such. And then you would have F orbitals, 1, 2, 3, 4, 5, 6, 7 of them, because they need to host 14 electrons. Be 1, 2, or hold on. I shouldn't do that. 1, 2, 3, 4, 5, 6, 7, 8, 9. And realistically speaking, these two orbitals are probably close enough in energy to actually have this one electron pop up here and pair up with another one in the 4F orbital, but I'm just not going to assume that because this is just a very rough kind of discussion without proper measurements. But the phenomenon of ferromagnetism arises when you actually have lots and lots of unpaired electrons within orbitals. And, there's a lot of different elements that have unpaired electrons, like, on their own. Like, if you just took the structure of phosphorus randomly, that has a structure that looks like this, atomically, where you have 1, 2 in the s orbitals for it, and then 1, 2, 3. It has 3 unpaired electrons, but phosphorus on its own is not a magnetic material. But that's because phosphorus bonds its electrons together, so that way everything is all paired. Now, in a metal atoms like dysprosium do form bonds to each other, but they are not very strongly directional. And when you have orbitals that kind of fucking look like this clown show, they don't really form good, like, really strong bonds that are like uniquely directional to the neighboring metal. It kind of more like makes bonds that's just kind of like, well, we can kind of share some electron resources here, yeah, but I'm still hoarding it mostly for me. And so you end up getting electrons that are still very free to move around in an unpaired fashion. And because electrons have charge and they are moving around this orbital shape, that I guess that's what an orbital is. I should have explained that. That an orbital is the probability cloud that an electron moves in up to like a certain probability cutoff. Given that an electron's a charged particle, it moves around in the shape defined by orbitals, 3D shape defined by orbitals. A moving charge makes a magnetic field, and so when you have metals that have all these unpaired electrons, then you end up having a magnetic metal. So that is all to say, dysprosium is not super surprising that it is a magnetic element, even in bulk. This is the same philosophy behind why iron is a magnetic element, and so is cobalt. And nickel, not exactly because of some other factors, but you theoretically could kind of make it there. Copper isn't magnetic because again, this orbital picture gets a lot more complicated when you really get into it. But for something that has just this abundance of unpaired electrons, this kind of rough back of the napkin explanation kind of covers why or how it works. So, thanks for sticking with me through that. That was quite an explanation there, even for me. Let's get back to the video.
Active element.
So where were we?
And with this
All right, magnets, and now we're gonna get some dysprosium shavings.
He also took some filings of dysprosium metal. You know, we tend to
look at how shiny it is under that oxidation.
Finely divided metal, and he could move
look at that. That's cool.
Around
it's
on
like Etch-a-Sketch
paper with his magnet underneath. I quite like that. But the exciting chemistry and magnetism we'll get to in a minute. Dysprosium metal dissolves quite easily in hydrochloric acid.
As many metals do. Look at that hydrogen get produced.
Neil and Brady had quite a lot of fun. Bubbles away, release of hydrogen, and the dysprosium chloride that's formed is completely soluble in water or weak acid. Fortunately, we didn't have to use that solution for our reactions because my colleague Peter Harvey lent us a whole bottle of dysprosium chloride, which he was using for magnetic experiments. And so we had a nice solution of dysprosium chloride. And we filled a whole series of tests.
Hold on, let me rewind the video. I was drawing that. I didn't notice if they showed off the bottle.
Chloride, which Harvey.
Oh, they did? Okay, that was... Okay, good. I had to make sure I got my stoichiometry right. It should be a +3 ion, but the rare earths can do weird things sometimes.
And we filled a whole series of test tubes to try different reactions. The first reaction was with carbonate solution.
A simple one.
And you get a nice precipitate of dysprosium carbonate. It's white. Most
well,
of
the reaction's already on screen.
Of the rare earths elements
simple kind of acid base-ish.
We then tried the hydroxide.
Yeah, it's not an acid-base reaction. It's a double displacement. But anyways.
And we got another precipitate that was white, but it looked slightly different. It's what chemists call slightly gelatinous, more like a jelly.
Sulfide.
Then we tried the sulfide.
So you notice some of the salts are soluble, some of the salts are insoluble. Dysprosium chloride is insoluble. All of these other ones they're forming are... dysprosium chloride is soluble, the other ones are insoluble.
And this is really quite exciting because normally when we try these tests...
And, you know, there's sort of prediction that you
when
can
nothing
do with
exciting
them,
happens.
but
And Brady
there are
says
certain
the professor
anions that
doesn't know
are
what he's doing. In all these
very
tests,
strongly
we
bonded
put
into the
a
metals, and they're going to
dysprosium
precipitate as
into a
solids. They won't
test
be
tube
separated by water.
containing whatever the reagent was.
So sulfur really
hydroxide,
likes to stick to
carbonate,
dysprosium, so
and
it's
so on.
insoluble.
We also
Hydroxides
did
do,
it with
carbonates
sodium
do,
chromate, which is
and
quite
chloride doesn't.
strongly yellow.
Ooh,
the
chromate.
solution.
Wow, that's going
And
to be an
when you
interesting
add
salt.
the dysprosium chloride, you get a precipitate of the dysprosium chromate.
Dysprosium chromate.
The
Good
solution
God.
is so coloured anyway, you don't see it very well. So we reversed it, filled a test tube with
Look at that yellow
dysprosium
cancer in a tube.
chloride and dropped in some chromate, and then you saw a beautiful yellow precipitate.
Doing it in reverse. Look at that.
Finally, not to disappoint Brady, we decided to do permanganate, which, as you know, is a very dark purple colour in solution, and we dropped some permanganate into the dysprosium chloride solution.
Ooh, they recorded that kind of weird on
and
accident.
nothing happened. So Brady was pleased. Professor wrong again.
Permanganate is a very soluble salt, to be fair.
What happened? You made us do that.
Yeah. We then thought we would add acid to all of these test tubes.
See if you can redissolve it again.
Dysprosium carbonate bubbled, releasing CO2 and dissolved. We added hydrochloric acid, so we were regenerating the dysprosium chloride.
Yeah.
Similarly, the dysprosium hydroxide dissolved up.
You can get many of these reactions to kind of go
And
in
the
reverse
sulfide,
just because of the
though there was also
you add enough
different
acid,
smell
then
of rotten
it really
paint,
wants to take away that
hydrogen
negative
sulfide,
ion,
which is
producing,
quite nostalgic to me.
like what
I
they're
used to
saying,
use
the hydrogen sulfide,
at
the
school
water,
with
the carbon
chromate.
dioxide.
It was interesting.
It'll redissolve.
because the solution
It no longer wants to stick to
colour
dysprosium,
almost instantaneously.
and the chlorine can come back
because
in.
chromate can, in acid
As second
solution,
pony.
can form dichromate. There's an equilibrium between dichromate and chromate. One is orange and the other is yellow.
It's a very
But
nice
then,
set of colors
just
there.
to snub Brady, when we put the hydrochloric acid and the permanganate, it went colourless.
Oh, there you go.
Not because of the dysprosium, but because hydrochloric acid reacts with permanganate to produce chlorine. But still, it was a nice colour change.
I've never
So we
combined
have a
those
series
before,
of
but that makes
reactions
sense.
Which really look nice and demonstrate that
Permanganate's a very
dysprosium
strong
has really
oxidizing
quite
anion,
similar
and chlorine
chemistry
or chloride
to
would like to be
the
oxidized to
other
some other
rare
things.
earths. And this
Or
is
could be
part
oxidized
of
to
the
some other
problem that the chemists in the 19th century had when they were trying to isolate this element. In fact, the name dysprosium comes from the Greek word, I think it's dysprositos, which means difficult to separate. Dysprosium was discovered by the French chemist Paul-Émile Lecoq, who also discovered gallium and samarium. He was really quite an interesting character. He wasn't a professional chemist. He didn't work at a university. He worked in the second bedroom of his two-bedroom apartment. Don't try separating elements in your bedrooms. The way...
But it worked so well for the people of the past. Anyways, I think they're about to get into maybe why the rare earth elements were so hard to separate from each other. And I can, thankfully, with this diagram up, I can still kind of summarize things without having to retread too much ground. The long and short of it is that, I guess I should draw this back in for F. All right, the long and short of it is that all of the rare earth elements, because they're busy filling up all these 4 f orbitals with electrons, what is known as the least shielded of the... hold on, I'll back up. So normally atoms ionize by losing their their electrons that have the most energy in them, such as their 4f or I need to start over again. Normally atoms ionize by losing their uppermost energy electrons. The uppermost energy electrons are the ones that are being added to every time you kind of increase the atomic number and go over to the next element over, which in this case is the 4f electrons. However, because of the fact that these 4f electrons are in that 4th tier of energy, much lower than the 6th and 5th tiers of energy, this also kind of is a rough proxy for how large those orbitals are. And so if you take this kind of f orbital example, this thing has a size compared to a d orbital, which might look something of like, hold on, if I could draw it well, something of like this size, so like much larger than it, and is kind of literally, I'm drawing it separate so you kind of get an idea of like the scale between these, but these would be literally on top of each other. So the 4f or the 5d orbital would be comparatively easier to reach than the 4f orbital. So those that one electron down here could come off first, actually. It's just easier to kind of grab, and they are not what is known as shielded from the actual atomic core of protons as much because they are further out. These 4f electrons actually shield the 5d electron from the proton positive charge in the core, so the 5D actually ends up being easier to pull off, even though it was added to much earlier and is at a lower energy, lower total energy. And then similarly, the same argument holds for a 6s orbital, which would basically just be a really big sphere that could encompass all of these. And so, since all the rare earths basically have this 5D 6s configuration, those are the 3 electrons that want to come off first, and they are pretty easy to rip off, and doing so gives empty shells for 5D and 6s, which takes away these big these electrons in these big spaces, far away from the nucleus, not well shielded, and just leaves the 4f to be like the new actual valence. So, in short, basically all of the rare earth metals are so difficult to separate from each other because they all like forming +3 ions of similar size, with similar orbitals being the valence shell left over being the 4f orbital. So, and then I guess there's like scandium and yttrium, but they're not using f orbitals, but they also like forming 3+ and are similar size by coincidence. So they all get mixed together. We call them rare earths. It's hard to separate out the different 3+ ions because they're all really almost the same. Yeah, so that's why it took so long to actually get dysprosium and others isolated.
He identified these elements was largely by looking at the spectra of the
tale as old as time.
When they were heated in a
burn the metal, see what the color produced is.
Some extra lines which he assigned
and be like, wow,
to dysprosium.
Never seen that anywhere else. It must be new.
To actually isolate the dysprosium was really very hard. I suppose in those days there was a huge driving force to discover another element, so people kept on doing it.
Yeah, I mean, if it was possible, you actually could. You didn't need a particle accelerator for it.
The more modern chemistry, and the real interest in dysprosium, apart from using it in alloys to make better magnets for things like wind turbines, has been in what is called single molecule magnets. You probably know
it is an area of research I don't know anything about.
On many computers, on hard disks, are stored magnetically. And over the years, the amount of space each bit that is stored requires has got smaller and smaller.
Yes. Thank you, Moore's law.
It still requires quite a large collection of atoms to store one bit. However, there are a number of new compounds which are so-called single molecule magnets, where just one magnetic atom in the middle of the molecule is enough to store this information. So
very
you can
impressive.
align the magnetic moment of that atom.
Seems very
and it
easy
will
to
stay
mess
there
with
and
as
won't
well.
flip back.
It's the problem.
Because
That's why you
otherwise
usually
you
encode it
lose
in
the
multiple
information.
So
atoms,
one
right?
direction
A big
represents
chunk.
a 1 and one direction
So
represents 0.
0.
Right, okay.
Well, people have not got as far as actually representing things, but they've got as far as making materials where the magnetic information will be preserved for a relatively long time. The first molecule that was made was by a chemist called Layfield at the University of Sussex in the south of England. The dysprosium atom was sandwiched between two C5 rings.
Surprised it's not
and it
more
had some
complicated.
extra
It's a
groups
fairly
here as
easy
well, so that each atom was
chemical
nicely
to make once you actually have pure
isolated.
dysprosium.
This molecule would retain its magnetism up to about the temperature of liquid nitrogen,
least I would think it's
which is 77
a lot of other
Kelvin,
metals can
the
take
boiling
that structure,
point of
so
liquid nitrogen. More recently,
you know, I figure someone would
a
have tried it,
group
right?
in Manchester, working with a group in Australia, have made a new compound which has a dysprosium
Ooh, now
atom
that's a complicated
sandwiched
looking one.
between two nitrogen atoms, and there's almost a straight line between the two nitrogens and the dysprosium.
I would call that almost
And
a
this
straight line. It's a
keeps
little
the
bit charitable.
dysprosium atom very well isolated, so once its magnetic moment is aligned, it doesn't lose it at all easily. This compound operates at a higher temperature. It still needs a low temperature, but I believe it's above
Pretty.
100 degrees
Wow.
Kelvin.
That is a
are
very
not
pretty crystal, I gotta say.
above
You usually
100
don't get
degrees
nice iridescent crystals like that. Usually it's often just one color, but that's like a really cool plate of that new dysprosium material. And fun fact, you get that iridescent color by thin film refraction of light. It's not that each individual piece of the material, like the material itself, is not actually that color. It's physics of light going through a thin film, and then partially bouncing off that thin film, partially bouncing off of the opposite end of that thin film / the like glass it is being held up against. And just the tiny difference in travel paths between those two lights when they come back together makes a new color. Hey Proto, welcome. You love iridescence? Yeah, no, it's a good effect overall, and I mean, it's physics is the best way to get it done, really. That's why you can have simple diffraction gratings are able to give, you know, so much different color just from pure light. Or in nature, that's the most common way actually for things to be colored differently. Like most butterflies don't have pigment in them. They have scales that are kind of thin film and spaced out to a certain point where the light that actually hits the wings refracts off of them and then recombines after that short difference in distance and creates, you know, blue butterfly wings or orange butterfly wings, etc., etc. No dysprosium in your butterflies, unfortunately, but, you know, the sometimes nature and biology is actually kind of cool. I've got to give it to biology sometimes.
Kelvin. The rare earths are not terribly rare, but at the moment, much of the supply of dysprosium
Hey, the
comes
point I
from
was making
China.
earlier.
Some of it comes from Myanmar, and deposits have now been discovered in Australia. There are quite a few minerals that contain
Don't worry, I'm sure some
dysprosium,
fuck-ass farmer in
but
Oklahoma is
it's
going
not
to
pure.
stumble on the
It's
world's
just
biggest reserve
of
one
several
day. It's
components
just how it works in
and
America.
not the biggest metallic component of a particular ore. So what is really the key to making dysprosium is to
I want dysprosium in a butterfly
separate
too.
it from a
But,
rather impure
you know,
ore
You'll have to be the one who
at a
engineers the
reasonable
dysprosium
economic
butterfly.
cost. And over the last 20 years or so, the price of dysprosium has rocketed up and down. I have no idea how much the sample that we were generously given is worth, but it is still quite
I
quite
mean, you
a
could just
rare
estimate, like,
element to
what's the
have
cost of
in the lab.
dysprosium per gram, and then measure it. Like, that would be a pretty good estimate, I would say. I have no idea how much it would be, but
our gallant technician Neil
$100
really loves
for that
is sprinkling
lump.
fine powder of the elements into a Bunsen burner.
Disproportionate because he only had one wing. Now you're thinking of Sephiroth, but metal. Slightly different guy.
Certainly,
I can see,
did not
Sephiroth
disappoint.
butterfly, it's a similar
We
thing.
weren't sure what to expect, but
It's a cool light show.
produced
I think I can
very
actually see the
bright
green and yellow
sparks.
sparks. I still think that Neil is crazy for just, open
One
hand near the
experiment
flame. Just throw the sparks in.
completely bleached out the video camera.
Don't worry about my hand getting burnt.
picture because the light was so bright.
Or the paper, for that matter, either.
I thought it looked really beautiful. I think together with some of the other rare elements fireworks, I'd really like to have a dysprosium firework as well.
Probably are dysprosium fireworks. I mean, most fireworks operate and get that little color crackly effect through metal shavings. Maybe dysprosium's not the most efficient way to make green. That would probably go to copper, but, I'm sure if you want a specific shade, you could get an expensive dysprosium firework.
We like to observe what happens in our experiments. And at the end, just before Neil was clearing up his fume cupboard, he noticed that some of the tiny particles of dysprosium salt on the floor of the fume cupboard, probably the oxide from when he burnt the metal fragments.
Yeah, I mean, it's not like it just goes away.
Had absorbed water from the atmosphere.
Oh.
These are so-called hygroscopic compounds. They absorb water from the atmosphere.
Interesting. Not a lot of oxides are hygroscopic.
In principle, not with dysprosium, but with other salts, you can actually get water from the atmosphere. And there are groups in California who are trying to make emergency water supplies for travelers, for soldiers.
Yeah, he does. He very much does embody science.
Compounds that will
The hair does a
attract
lot of
water
heavy
from
lifting.
the air. They've even got water from the air in Death Valley.
Thanks for showing your support by watching.
Huh, interesting. Yeah, no, I didn't know dysprosium oxide would be hygroscopic. I wouldn't have predicted that. I mean, in one sense, it's kind of like, well, oxides, they kind of have the oxygen necessary to make hydrogen bonds with the water, and they might want to pull on those hydrogens, but for the most part, oxides just don't, like rust isn't pulling in water. That's iron oxide. It's not pulling in water from the atmosphere. Most metal oxides you encounter just don't really care about oxygen, or about water in the atmosphere. But I guess dysprosium oxide's different. Maybe because the oxygen... It's probably because the oxygen is not actually bonding very strongly to the dysprosium. Oxygen is so tiny compared to dysprosium, it has a hard time actually bonding in. So maybe it's like, it starts to see the water vapor is like, ooh, I could actually go for some of that instead, actually. Cool. All right, well, I learned a couple things about dysprosium even from that, so I'm a happy man. All right, let's get to the main attraction for today. Or at least one of the two main attractions for today, because it is time to get to the Coca-Cola discussion. I am so sad that it took me this long to actually get to reacting to this video, but it was just one of those things where it's like, when was the release date again? Yeah, January 8th, which I'm pretty sure was like maybe a day or two after I did my January reaction, and I'm like, I really don't feel like doing another one this January. So now, hey, here we at now we in February, and we're gonna get to replicating Coca-Cola apparently. Okay, so this is LabCoatz. I do enjoy this channel a good bit. I think I've mentioned him a few times before. He was the guy who made the real stinkiest compounds in the world, making a bunch of organoselenides in the back of some national park parking lot, and yeah, they were real obnoxious, smelling like rotting garbage. And I respect anybody who has the wherewithal to make some compounds that are that horrifyingly smelly and in the back of their car, no less. So he does some pretty cool stuff overall, and I'm very interested to see if he really actually did get to perfectly replicate Coca-Cola. Of course, you know, I'm guessing this is probably just him comparing his flavor profile or what he tastes in his recipe versus the Coke recipe. But it's still a pretty impressive feat either way. And, you know, it took the internet by storm as well when it came out. Brother got 8 million views for this, so mad respect regardless. Yeah, they made Coca-Cola real again. Yeah, no, dude totally added illicit compounds from the cocoa plant in there again. Yep, definitely. Super real. I'm pretty sure that compound can be made in one's stomach if they eat enough crappy leftovers in the fridge. If you had enough, I know you jest, but if you have enough organoselenium in your body, it'd definitely already be toxic and you'd be keeling over. And fun fact, interesting thing about selenium. So you know how? Well, you might not know. Maybe I can get a picture up real quick. Hold on. I don't want Firefox accidentally. Oh, wait, hold on. No, I could do this. And then stop this. And then just give me a periodic table. In the periodic table, you actually have that group 16. Yeah, group 16 elements. Oxygen, sulfur, selenium, etc. So because these are all in the same group, your body kind of has basically, the biology has made it so that way your body is tuned to basically understand the difference between oxygen and sulfur, because both are key components in many organic molecules. And your body obviously picks up that sulfurous things are smelly. That's how we know, like, a lot of sweat is smelly. Certain like compounds from plants are smelly. Stuff like stuff from like broccoli, asparagus, all that can be smelly. I think some of that has sulfur in it, or high sulfur content. However, your body is kind of stupid and doesn't actually go further than that because it doesn't really encounter selenium, tellurium, polonium in its given life. So selenium compounds are as smelly and horrifying as they are because your body basically just interprets it as big sulfur, and tellurium as even bigger sulfur. And so if you end up having selenium or tellurium even in trace amounts in or around your body, it is said that you will smell like, and perhaps even smell on your own breath and skin, garlic odor for a very, very, very long time. Because even in tiny amounts, your body is going like, oh my god, there's so much sulfur in the area, because your body's a fucking genius and can't tell the atoms apart. Anyways, there's probably not selenium in Coca-Cola's products. I mean, I don't know, we'll see. But I would doubt that, considering it does not smell like a dumpster. It just kind of smells like sugary brown liquid. Let's go.
Hey everyone, welcome back to LabCoatz. Did you know Coca-Cola is the world's most popular non-alcoholic beverage? That's a little tidbit I picked up as I studied literally every aspect of this drink for almost a year at the cost of my own sanity, but I digress. Point is, Coca-Cola is kind of a big deal. Practically every human being on the planet knows what it is. And yet, despite existing for almost 140 years, only a handful of people actually know what it's made of. As a matter of fact, the Coca-Cola secret formula is one of the most tightly guarded trade secrets to ever exist, with protective measures so extreme that they're almost laughable. Seriously, they have a giant steel vault that they show off on guided tours. Does that not sound like something straight out of SpongeBob?
There's not the actual vault they show off on a guided tour.
And if that wasn't enough,
it's probably a dummy vault.
Are all shipped unlabeled and from entirely different facilities, who are kept almost entirely in the dark about what they're making. So much effort, all for a soft drink that the company half-heartedly promotes with horribly out-of-touch AI commercials. Wouldn't it be funny if somebody managed to steal the secret formula right from under their noses?
Yeah, Plankton, do it. Give the people what they need.
With the exact same flavor, and then tell absolutely everyone on the internet how to make it themselves?
And the best part is, it's not even illegal because they did not patent their formula, because if they patented it, it would then be public knowledge, so they had kept it as a trade secret, so that way it's not public knowledge. But because they didn't patent it, they don't own the rights to the formula.
To most sane people, this probably sounds like a fool's errand. After all, many have attempted the quest and invariably came up short.
Yeah, it's their own downfall.
I tried all their formulations, none of them tasted like real Coke. So, is this even possible? Well, in theory, yes. One article from 2016 theorized that the recipe could be deciphered with the help of mass spectrometry.
Yep.
Although the author basically concluded that only a major group like Pfizer would have the time and resources to actually do so. Guess this was before science YouTubers got serious.
Yeah, science YouTubers weren't buying...
YouTube friends.
Science YouTubers weren't buying fucking $200,000 instruments from China to set up in their own backyards. You know, it just wasn't part of the culture yet.
With 2 different kinds of mass spectrometers. And one even happens to be a college professor. Yeah, we're coming for you, Coca-Cola.
Oh, but Zach, Coca-Cola uses coca leaves. You can't possibly hope to replicate it without...
Have you heard of chemicals? I'm aware that whatever I make won't be absolutely identical down to the trace contaminants. But if I add all of the major flavoring agents that are detected in real Coca-Cola, I should get something that tastes like Coke, regardless of if it came from a coca plant. And spoiler alert...
Dude.
Yeah, I can't even tell. Even though I know already, I can't even tell.
I wasn't expecting it to taste so much like Coke. Oh my god.
This approach actually works pretty freaking well. And in regards to legality, well,
there's the thing I just
Coca-Cola
explained.
hasn't actually patented the recipe. Seriously. Doing so would require them to expose what they're actually patenting, and that's obviously not something they want to do. Consequently, unless I try marketing my own product under the Coca-Cola name,
But
there's
chocolate in
really
your
nothing they
Coca-Cola.
can do about it.
It's both brown.
So, what are we waiting for? Let's get cooking. Now, believe it or not, we already know over 99% of Coca-Cola's makeup, at least by weight. A
And
liter of
it's
Coke contains
probably
roughly
water.
110 grams of sugar, 96 milligrams of caffeine, and 0.64 grams of phosphoric acid, based on...
I still think it's kind of crazy that sugar does in fact contain, or not sugar, soda does in fact contain phosphoric acid. Like, phosphoric acid's a pretty nasty, strong acid in the lab space. Like, not only does it smell really bad and have a very pungent feeling anytime it hits your mucous membranes, it is rather corrosive. I'm shocked. I mean, it makes sense you dilute it enough, it's not going to be that harmful to you, but like it is still like one of those things where I'm like, I'm drinking this? Like, this is a lab chemical? This doesn't feel right.
pH measurements and other scientific analysis.
But, you know, your body needs phosphorus,
It
so...
also contains caramel color, which contributes important
caramel
flavor compounds
color.
like furfural, in addition to the cola's rich brown hue. What we don't know is what makes up the last ingredient, natural flavors. This is where the real battle begins. As of 2025, only one of the natural flavors can be definitively verified, decoconized coca leaf extract. The Stepan Company in New Jersey is one of the only American companies licensed to work with coca leaves. And guess who they sell the extract to once the cocaine is removed?
You'll never guess who
Coconut
they sell the
extract
cocaine
was
to.
Also used at one point, but it was phased out in favor of refined caffeine. I tried finding my own source of cocaine-free coca extract, but companies like Power Leaves never returned my emails, and the package I bought from this definitely not sketchy Peruvian website got seized at the border. So basically I was at square one like every other non-Coca-Cola entity, which meant I had to work up the entire flavor profile from scratch. At first, I thought this might be fairly easy. I mean, several cola recipes are already published, including the original Pemberton Coca-Cola from 1886, so I figured it'd simply be a matter of tweaking these until I got something that fit. Long story short, I was very,
Yeah, if it
very
was going to be
wrong.
that easy, it
As a
probably
starting
would not
point,
have been easy
most
to...
recipes call for
someone
the
would have already
following
else
set of
made the
flavors.
video.
Orange, lemon, lime, coriander, nutmeg, cinnamon, vanilla, and neroli. A few other
Neroli?
ingredients that get suggested include black pepper,
What the hell is
lavender,
neroli?
clove, and kaffir lime leaf. So I bought all these flavors as essential oils from reputable vendors.
Okay, actually, no, I need to look up. What the hell is neroli? That's the only one of these I haven't heard of before. Neroli. Neroli is a essential oil produced from the blossom of the bitter orange tree. Okay. Orange blossom water. Floral oil. Okay. All right. Okay, so it's basically bitter orange, maybe not extract, but bitter orange blossom aromatic Extract. Okay, alright. That's at least something.
Using essential oils in food might sound a bit strange,
No?
but rest assured this is fairly
Doesn't
standard practice in the
sound
food
weird
and
at
beverage
all?
industry.
Okay, to the people who aren't weird essential oils cure everything wonks, no, that sounds pretty normal that essential oils are, in fact, in food. They are maybe... Now, this might be a shocker. They are oils that come from the foods that you eat or get from nature. Now, I know you're probably, like, standing on the top of your seats from that, but, like, if you've ever thought about what is in a lime rind and why a lime rind feels maybe just a little bit greasy if it's not wet, you know, you might have hit jackpot there.
As it allows for very precise and repeatable combination of flavors. To run my early trials, I would measure precise volumes of each oil using a micropipette and combine them in a small vial. Once mixed, the required amount of flavor oil would be dissolved in roughly 1 milliliter of food-grade alcohol, which helps it disperse into the soda instead of clumping into droplets.
Well,
this
that's
was an issue I
probably
faced when I made root beer
throwing
from
off
sassafras oil
everything,
a few years ago,
given
and
that
the
there's
ethanol
no
practically
alcohol in
eliminates it
Coca-Cola.
without throwing off the flavor. Finally, the flavor mixture will be measured
I
and
guess
added to
so.
a predetermined
Alright,
volume
if it's
of soda,
small enough.
which was made with the established proportions of acid, caffeine, caramel color, and sugar. Pretty straightforward. Initially, I attempted
You're
to use
allergic to
something
limes?
called
Wow, damn,
orthogonal
that
array to
sucks.
perform my analysis.
I love limes. To be allergic to, I don't think it's limonene, because lemons have lemonine? No. I can't remember what the lemon compound is called. Oh well, but oh yeah, that's right. You're you're whole entirely allergic to citrus. I don't know why. I know you're allergic to citrus. That was in my mind, and then you said just lime specifically. I'm like, oh, I didn't know that. And it's like, well, duh. If limes, it's specifically the skin. Huh. Interesting. My guess is probably the citrus allergy. Then is there's some kind of protein in the citrus itself, just like the citrus family. It probably doesn't do very well with that. I should look into that later, because I already told Grim that, like, you know, his apple skin allergy is like a specific protein in apple skin that, like, is irritating to people with an apple allergy. But with the citruses, citrus allergies are so common. I should look into that.
Nighthawk and Light has an excellent video explaining how these work, which I highly recommend you check out. But basically, an orthogonal or Taguchi array is a type of mathematical table that allows you to find meaningful correlations with a relatively small number of trials. In my case, I was hoping to determine which flavors contributed the most to the flavor of cola.
Guys, I hated stats. I'm not good at
Unfortunately,
stats.
the human mouth perceives flavor mixtures
I was a calc
in really
guy.
complicated ways, so my results were highly inconclusive and often disgusting.
That's a gamble.
That said, I did actually learn a lot by doing this.
Wow, no,
In
you're
terms of
really
flavors,
sensitive to that.
nutmeg,
Damn.
cinnamon, and
It's
coriander
probably
seem to contribute
just,
the
I guess, a
most to
couple
the iconic
compounds
cola
then,
flavor,
maybe, for you.
but not without a strong citrus base.
Sorry, what is
seem
it
to
saying
do a lot
here?
by doing this. In terms of flavors, nutmeg, cinnamon, and coriander seem to contribute the most to the iconic cola flavor.
Huh.
But
I'm not surprised with the cinnamon and nutmeg. The coriander is a little different. I mean, coriander seeds are a little bit kind of on that fresh, zesty, citrusy side, but I always assumed that was mostly just the acid and the sugar.
not without a
And,
strong
you know,
citrus
the
base
citruses.
composed of lemon and lime. At the same time,
Citri?
flavors like neroli and lavender just didn't seem to work in the modern profile. They added a strong floral note that isn't found in today's Coke.
Yeah.
And also
Today's
made it taste
Coke is
like artificial
artificially
sweeteners were being
and
used. And despite
Today's Coke is artificial, extremely thin, and tastes like it's making your mouth a weird, semi-sterile environment.
showing up in most recipes, orange didn't really seem to fit either. At least not in the large amounts that are usually suggested. 1 to 2% ended up being the sweet spot, and while modestly important to the flavor, higher amounts would begin to throw off the citrus notes. Of the other flavors I tested, Kaffir lime leaf was by far the most out of place, since it basically tasted like citronella. Clove was similarly overbearing and noticeably different from the spices found in Coke.
Yeah, clove maybe is a bit
while
too
black pepper and
Thanksgiving-y for
vanilla
Coke.
contrastingly seemed to
And
do
pepper?
very little.
Hmm?
I mean, if I really boosted the vanilla, it was detectable and the perceived sweetness would go up, but black pepper mostly just seemed to accentuate the more earthy flavors already found in nutmeg.
I would also say there's kind of a giveaway that there is just vanilla Coke sold, and that is a separate flavor. It would probably be very noticeable if regular Coke had vanilla flavor.
Now, while I did gather at least a rough idea of what's in Coca-Cola from these early trials, I still had no idea what the correct ratios were, or what ingredients I was missing. So to find out, I cracked out my secret weapons: scientific papers and chemical analysis. In terms of analysis, Vince from Neptunium and Ben from Mass Spec Everything agreed to analyze Coca-Cola, my ingredients, and a few similar sodas like Pepsi using their mass spectrometers. These machines essentially take a tiny sample of whatever you want, split it into chemical fractions using either a liquid or gas chromatography column, and then analyze each fraction by ionizing and firing its components through a magnetic field.
Yeah, God, we're already 1 hour into the React stream tonight, so I'm not going to go over the entirety of how a mass spectrometer works, but what he says is fundamentally correct. It's like the chromatography column will separate your things by polarity, and then once it gets to the ionizer, it ionizes your separated things, sends it through a magnetic field, and your magnetic, and I guess the only thing he hasn't elaborated on is the fact that the magnetic field will make it so that will be varied, and depending on what the strength of that magnetic field is, only atoms of certain masses or ions of certain masses are actually allowed to make that bend and not just crash into the walls. Only certain masses will make that bend and go to the detector. But since that field is changed over time, heavier or lighter atoms or ions will be able to make it to the detector, and that's when the detector is like, oh, well, something hit at time equals 49.2x whatever seconds, and that means that this is something with a mass of 15 units or whatever. That's how that works. There are also, this is like the simplest and oldest version of a mass spectrum. Or mass spectrometer. No one uses these days. This is just the fundamental principle that everyone's taught of. Everyone uses a quadrupole mass spectrometer now at minimum, and then there are other way more complicated mass spectrometers out there. One of these mass spectrometers, the earliest mass spectrometers that use this just one electromagnet and bending around a corner fundamental principle, these would take up like entire rooms of space, like 700 square feet of space kind of amount of space. There's a good fucking reason no one uses these nowadays, but they're also just the easiest one to discuss the concept of, because if you want to discuss a quadrupole mass spectrometer, then that means you have to discuss 4 electromagnetic poles alternating in different sequences and doing a bunch of other bullshit that I only barely remember from my time in physical chem. So yeah, off the table, me going into a further explanation, but that is the general gist of how mass spectrometry works. It's like an anti-mass spectrometer, expect normal matter. Yeah, no, essentially, yeah. If we wanted to make an antimatter spectrometer, we could. There's no such thing. As far as I know, there's no such thing as an anti-mass spectrometer. I know it's a half-life thing, but if I don't know anything that could possibly have negative mass quite yet, and I don't think physicists do either. Shockingly enough.
Much like a prism splitting up light, the magnetic field splits up ions based on their mass.
He already said it.
A sort of fingerprint that can be used to
I didn't need to
identify what
say
chemical was ionized.
Well, I elaborated.
That's the explanation, and this is the exact chemical makeup of Coca-Cola.
Yeah, so there are a couple other things here. Saying it's exact is a little bit generous, which I'm sure he's going to get into. Because while this tells you what the masses of something is, I guess I can get into a little bit more. So when you have something on your, actually, wait. Okay, so this is not actually the mass spectrum. This is the liquid chromatogram. So how we were saying first, you had to have something that goes through a chromatography instrument to separate everything out first. This instrument is essentially saying, okay, you're getting some things coming up, cropping up before 10 minutes, some things cropping up around 20, some things around 25, some big thing around 30, and then almost nothing but solvent until you get to around like 55, 57 minutes or so, and that's where you then get another tiny thing. This doesn't tell you the chemical makeup, but this is saying, okay, you're going to have different components splitting off at these parts. Each one of these peaks corresponds to either A, different component, which is the most ideal situation, or B, which is usually what happens and what causes trouble, is there are multiple things that are around the same polarity that get pulled through the chromatography instrument around the same rate. So, I mean, I guess quick explainer again. Polarity is just the electromagnetic difference between different sides of a molecule. Water is your most common polar molecule. Oxygen is highly electronegative on the periodic table. Again, this is a whole other topic. I don't need to get in the rabbit hole for it. We've kind of explained before. Hopefully you kind of know from previous times or from your chemistry experiences in school. But take the word on it. Oxygen's more electronegative than hydrogen, means that oxygen wants the electrons more. So in the molecule, you end up getting a slight bias towards negative charge, represented by the end of the arrow, going towards the oxygen side, slight positive charge going towards the hydrogen side. You can have similar things with a compound like acetone, which has carbons at the bottom, which also has a positive polarity like this. So say in a mass spectrum or in a liquid chromatography instrument, you'll end up having liquids being separated by their polarity. And yes, each molecule does have its own unique polarity, but say you have a molecule that looks like this, and you have then another molecule that ends up looking like 1, 2, 3, 4, like this. Yeah, the instrument's probably not going to be able to tell these two apart because the polarity difference between these two is negligible. You could measure a difference with the right equipment, but it would be so small, especially in liquid phase, that like these two are just going to come out and go into the mass spectrum around the same time. And you know, they'll weigh a little bit different because this one has an extra 13 atomic mass units thanks to this methane group at the end. 15 atomic mass units, not 13. But, you know, they're going to elute together in this initial peak. And then that's not also to say, like, depending on what you're doing to ionize your sample for mass spectrometry, you could get things breaking apart. So you could just end up having these 3 carbon fragments, and maybe this could somehow form a 3 carbon fragment too, or maybe these things don't actually come out as just whole molecules that have different masses. Maybe they just completely split apart. So you end up getting lots of variation, and that's why decoding a formula from scratch backwards like this is really difficult. You not only have the difficulties of what if you have similar components that come off the chromatogram at around the same time, you also have the difficulty of, well, what if those components within around the same time then go to the mass spectrum and are really hard to distinguish from each other there. And even then, you can kind of put pieces together and like say, well, you could maybe have something of this mass, but it's then also harder to say because you're just kind of thinking and putting some ideas together without really any ability to get chemical structure information. For that, you need NMR, and I'm guessing we're going to get to NMR later, so I'll shut up for right now.
Let's dissect its secrets, shall we? The dominant peak we found was something called alpha-terpineol, which mostly arises from the acid-catalyzed hydrolysis of limonene and pinene, and it hints that citrus oils do in fact make up a large portion of Coke's flavor. The next major peak is actually the remaining limonene, followed by 4-terpineol and fenchol. Cinnamaldehyde, saponine, and carine were also detected.
Wait, hold on. I might not have...
Limonene and pinene. Alpha-terpineol, which mostly arises from the
okay. That alpha-terpineol is from that limonene, that pinene that's found in the other peaks that get hit by the
next major peak
acid from the phosphoric acid.
Followed by 4-terpineol and fenchol. Cinnamaldehyde, saponine, and carine were also detected, indicating the presence of cinnamon and nutmeg. And finally, we found eucalyptol, borneol, furfural from the caramel color, and ethyl levolinate. Levolinic acid and its esters form when sugars like fructose are heated under acidic conditions, which suggests that Coca-Cola undergoes heating at some point during its production.
Yippee!
Now,
heating.
This is all well
Probably
and
to
good,
kill bacteria
but
and stuff.
Unfortunately, we couldn't pin down the exact concentration of each component using this data.
You have to
a mass
calibrate
spectrometer's
it.
output is given as a plot of relative intensity, not concentration. If you want concentration, you usually have to do a lot of math and other testing to figure out how different chemicals interact with the machine.
You don't do math on YouTube.
So, instead of relying purely on the mass spectrometry data we collected, I chose to also lean on the data from this article in the Journal of Agricultural and Food Chemistry. This table in particular listed pretty much every flavor found in Coca-Cola, and even gave their measured concentrations. There were a few flavors they left out, such as fenchel, but I figured once the concentrations of other ingredients were determined, these secondary flavors would be easy to dial in with the help of mass spectrometry. I won't be going through every chemical on this list, but there are a few I'd like to point out that reveal important information about the secret formula. Obviously, cinnamaldehyde and vanillin can be directly correlated with cinnamon and vanilla, so we can check those off as part of Coke's recipe. Limonene and alpha-terpineal are also present, along with aldehydes like octanol, nonanol, and decanol, which collectively signal the strong presence of citrus oils.
Oh, okay.
This is all stuff we mostly knew. Things get interesting, though, with linalool and the various forms of eugenol. Eugenol and its esters make up 80 to 90% of clove oil, which is one of the suggested ingredients that people reference from time to time.
However, you thought it tasted off.
The concentrations found in Coke are only enough to account for the traces contributed by nutmeg and cinnamon oils, which are much more definitive ingredients. And since clove oil threw off the flavor in my early tests, I think it's fairly safe to rule it out as a potential flavor.
Oh, okay.
Sticking with
so the
ingredients we
other
already discussed.
So while those two, or while that eugenol is found predominantly in clove oil is carrying other things that make it taste weird, and you can get enough eugenol in trace amounts from other materials by adding those in, rather than adding in eugenol through clove oil as a main source. It comes along as a byproduct. All right, Proto. Thanks for checking in. Have a good one.
Linalool also rules out a few potential flavors.
Linalool is also a fun compound because it's typically used as a one of the classic general chemistry demonstrations of a compound that undergoes chemiluminescence, i.e., when doing a certain reaction, it will actually produce light. It's kind of, a glow stick, basically. Not many chemistry reactions do that. Why? I'm not exactly certain. That would require more physics knowledge from me, but it's an interesting one that you can get from a fairly common molecule, all things considered, and so it's a cool demo. It glows blue.
To explain how, though, we need to talk about enantiomers.
Sadly, I've never done it.
Basically, for a molecule like linalool, two mirrored versions exist, R and S. You can flip them around all you want, but no orientation will make them identical.
Left and right hands.
Interestingly, the R enantiomer
Can't stack your left and right hand on top of each other.
Lavender and neroli oils, while the S enantiomer makes up the majority of coriander oil.
Oh.
And according to the study, Coca-Cola contains mostly S-linalool, with the amount of R-linalool only being enough to cover what would come from the citrus oils. Some might argue that chemicals like neral and nerol signify the presence of neroli, but this simply isn't the case. These compounds are found in citrus oils just like linalool, meaning we can pretty definitively say neroli and lavender are not ingredients in Coke. The last chemical I'm going to bring up...
Interesting. Okay. I thought you said the lime one earlier, or the whatever the fuck the fancy lime leaf was called is not in Coke. I know he said lavender probably wasn't in there from his taste test, but interesting. Okay.
Is acetic acid.
All right. That's odd. It definitely does not taste like vinegar, but I guess it could probably be doing some kind of reactions there. Coca-Cola certainly is acidic as hell, despite having only that little bit of phosphoric acid in there, so maybe it's not entirely surprising that there's white vinegar distributed throughout.
To me, this one was kind of a shock, especially with it being the third most prominent flavor by mass.
Wow.
My first thought was that it was simply arising from the acid-catalyzed breakdown of acetate esters in the cola. But after talking with Darcy over on the Art of Drink channel, and seeing it in an actual recipe from the 1950s, I'm almost certain that's being added deliberately. To be clear, the amounts being used are in the range of parts per million, but I still find it kind of funny that vinegar is probably one of the secret ingredients. With the major flavoring...
Well, you know what else I'll say? It's probably not too surprising that, or one thing that makes it less surprising for vinegar to be in Coke is just the fact that Coca-Cola's recipe is so old that they were probably just grabbing whatever the fuck they could from commercially available sources, and yeah, no, vinegar's been produced en masse for a long time, so it wouldn't be surprising to me if they were just like, well, we need something extra to make our cola extra good and delicious, and they just said, hey, man, let's put some vinegar in it, and someone's like, you're a fucking genius, Bob, you're getting a promotion.
Compounds identified and correlated with existing ingredients, I set up an Excel spreadsheet to make iterating my recipes a bit easier. A mixing calculator would basically take the volume of each oil being added, determine how much of each component was present, and then compare that data with the Coca-Cola numbers.
I never want to do math in an Excel spreadsheet ever again. The last time I had to do serious math in an Excel spreadsheet was me staying up all night for my analytical chem classes. Literally one of the only all-nighters I've ever pulled in college. Ugh.
Once everything was matching, I would take the recipe, log it on a separate tab with notes about the soda it made, and finally rank how close it was to real Coke. Unfortunately, while most of the flavor compounds could be easily connected to at least one of the essential oils, there were a few that just weren't showing up on the mass spectrum. Specifically, fenchol and forterpineol.
Well, depends. What's your mass spectrum? What are you doing? Are you using electron impact? Because I could definitely see both of those collapsing to electron impact. It's fenchol's very strained. That bicyclic ring conformation is not exactly the most stable out there. And terpineol has plenty of opportunity to kind of rearrange, ditch the OH, make some kind of fragment open at that tertiary carbon center where the OH is attached to.
Alpha terpineol was also on this list, but after modifying my soda preparation to include heating, there was more than enough of it to go around. For the fenchol, I simply resorted to buying the raw chemical. But for forterpineol, I started down a completely new rabbit hole.
Why does he just add the raw chemical? I mean, I guess like you said earlier, if you can't buy coca leaf extract, you maybe just have to source a couple things extraneously.
You see, the taste of Coca-Cola can be divided into a few main groups. The two we've tackled so far, and the two most people stop at, are citrus and brown spices, along with less pronounced subgroups like caramel and vanilla. What most people tend to overlook are the more green, fresh flavors that seem to come from the coca leaf. Without these flavors, you tend to end up with a more spice-centered drink like Pepsi.
Based.
So, for my source of forterpineol, I decided to go with an essential oil that I felt would reintroduce those missing flavors. Tea tree oil. By mass, this stuff is close to 50% forterpineol, and most of the other chemicals it contains match up with those found in Coca-Cola, so it doesn't really mess up the mass spectrum. When I began using it, I noticed an immediate improvement in the flavor, although it never fully replenished the missing freshness. Overall, it was more like drinking Diet Coke than regular Coke, and no amount of tweaking or adding essential oils seemed to change that.
Interesting, considering that basically means the way to make regular sugar taste artificial, taste like an artificial sweetener, is to use pine oil with sugar.
Spent months adjusting the recipe,
That's
testing
not
the
how
ingredients,
actual chemistry
and
works,
forcing
but...
family members to taste my experiments. Eventually, my original soda stream gave out, and I had to buy a second.
A very willing family member to be like, yeah, sure, I'll eat your lab-prepared chemicals. Okay, thanks, son. Hope you're not trying to poison me.
This is starting to become unreasonably expensive.
Starting?
I tested cassia cinnamon versus cinnamon leaf, different versions of nutmeg and lime, heating and aging versus not, even adding trace flavors like isopugol. Heck,
Ew.
I even tested completely random flavors to see if they'd fill in what was lacking. They never did. After a certain point, I was pretty close to throwing in the towel. Maybe people were right to say that Coca-Cola is impossible to replicate without coca leaves. And then, the answer finally hit me.
You're gonna grow the plant?
Coca leaf extract is essentially a type of tea, and teas contain tannins. These tannins possess a dry, astringent taste that can help mask sweet flavors. And since they're non-volatile, they don't usually show up on gas-based mass spectrums.
Okay.
Explaining how I missed them for so long.
Yes, that would kind of explain things. So, I guess a part I left out there with the chromatography in a mass spectrometry is that, yes, you have to separate things on the chromatogram. First of all, if you're using liquid chromatography as the first step, yes, you have to separate it using liquid chromatography. But then once you actually get to the mass spectrometry, you have to boil those liquids that you have left over and get them into the gas phase, and you'll get the solvent into the gas phase, but you're not going to necessarily get the you'll usually end up getting whatever thing you dissolved into the gas phase. But if it's so averse to actually boiling and getting into the gas phase and melting and vaporizing and all that, it's not going to show up at all. So his hunch on tannins makes sense. It wouldn't have shown up in the results, so it's a good thing to test.
Best of all, they're sold in a purified state for winemaking, meaning I could quickly get a hold of a sample and test out my theory.
I'm kind of surprised on that, given that, usually wineries hold themselves high and mighty about the fact that their tannins are so wonderfully sourced from these artisan grapes and this this barrel that's been used since the age of King Charles III, and that kind of pretentious shit. You just fucking add tannins.
Worth it. This is the mass spectrum of Coca-Cola, and this is the mass spectrum of one of my replicas.
It's sort of nearly identical. I mean, you got a couple other random streaks of crap around like 33 and 53, but I mean, it's not too bad.
They're nearly identical. And the flavor?
Oh, let's see. What was his little note there?
Mine
has more furfurols, less alpha terpenol, and Angelica lactone. What the hell is that? From acid-catalyzed, heat-driven rearrangement of the livolinic acid. Minor differences. Sure. And then the blobby area is just noise. Uh-huh. Yeah. Well, okay. Given that, this spectrum, you can actually see the baseline kind of ridging up and down a lot more. Maybe he just didn't run a concentrated enough sample, but still, it's... Would have wanted to see better data for that to confirm.
Nearly identical. And the flavor, well, what can I say? It tastes like Coke. There are tiny differences, of course, but honestly, this stuff is closer to classic Coke than Coke's own glass bottle or Diet Colas are, and infinitely closer than any other replica. It definitely checks out as Coca-Cola, at least to me. We'll get to other people's reactions and opinions here in a minute. But first, let me show you exactly how it's made.
Hell yeah. Get the recipe book ready, boys. You can start making Coca-Cola at home for only the low price of probably several $100s to buy a whole shitload of essential oils, a soda stream, caramel color, and a couple of other components. This is very much worth it.
Brief spoiler, the startup cost for this recipe can be kinda high, unless you have a pre-existing stockpile of essential oils and accurate measuring equipment. Once you have everything,
can't forget about the measuring equipment either.
Produce a bulk flavor solution that will last for years.
Still fun,
allow
though.
You to create servings of Coke for mere pennies. No more paying a company that won't even pay real animators. In terms of hardware, we'll need a mass scale, an adjustable micropipette that can accurately dispense up to 1,000 microliters, a 50 milliliter graduated cylinder, some 1 liter storage bottles, and some kind of heat-resistant glassware for making the syrup. Resist the temptation to use metal cookware, since phosphoric acid can attack it and dissolve less than healthy metals into the soda.
Yeah,
There's a reason soda cans have that plastic liner.
Phosphoric acid's pretty
Finally,
nasty.
You can also use a magnetic stirrer for mixing, as well as a 1 liter volumetric flask to make the dilution steps a bit easier. For ingredients, we have all the essential oils seen here: sugar, carbonated water, caffeine.
Wow. Okay. That's a lot.
Caramel color, food-grade alcohol, 85% phosphoric acid, glycerin, wine tannins, 5% vinegar, vanilla extract, and fenchol.
Wow. Yeah, okay, let me read out the whole thing here, because he kind of abbreviated some of it. Carbonated water, 104 grams of sugar, a milliliter of flavor solution A. Flavor solution A is 20 to 21 milliliters of the following oil mixture to 1 liter using 95% ethanol, 45.8 milliliters of lemon oil, 36.5 milliliters of lime oil, 8 milliliters of tea tree oil, 4.5 milliliters of cassia cinnamon oil, 2.7 milliliters of nutmeg oil, 1.2 milliliters of orange oil, 0.7 milliliters of coriander oil, 0.6 milliliters of fenchol. You want 1 milliliter of this. Flavor solution B. Dilute the following ingredients to a volume of 1 liter using water. 320 milliliters of Shank's caramel color. Shank's must be important. 175 grams of glycerin. Less can be used. 45 milliliters of 85% phosphoric acid. That's the really dangerous one to actually, have around. Maybe this is why you don't want to make Coca-Cola at home. 10 milliliters of vinegar at 5% acidity, 10 milliliters of vanilla extract, 8 grams of wine tannins, can use more, 9.65 grams of caffeine. That doesn't feel specific. I feel like there's maybe a different group of wine tannins you could end up grabbing on accident, but oh well. Yep. And then 10 milliliters of that flavor solution B. That's pretty impressive. That is pretty impressive, all things considered. But I think, I would prefer not to have a flavor solution B that is still has enough diluted phosphoric acid to probably be corrosive and harmful.
Quick note, Fenchel
He's not
melts
sitting
just
around.
above room temperature, so you might need to warm it up in some hot water before beginning.
Huh.
I bought my sample on Amazon,
Cool.
and after testing it, I can confirm its flavor is present in Coke, so use it if you can. For caramel color, I used Shank's brand, but other varieties like Durkee should work just as well, as long as they're composed of actual caramel color and not a mix of red and green food dyes. If you don't use Shank's though, try playing with the amounts you add to get the right color. Also, keep in mind that we are working with chemicals here, including a few that are mildly hazardous. So, for your own safety, wear gloves, measure accurately, and don't taste any of the unmixed ingredients. The first step is to
But if going to be food, why can't not eat original things? That's because dosage matters. You wouldn't want to have 100% acetic acid, even though that is just concentrated vinegar. That's bad for you.
prepare what most people call the 7X flavoring, which is the mixture of essential oils and alcohol that make up the Coca-Cola secret formula. To be clear, what I'm about to share is not the Coca-Cola secret formula, since I failed to utilize decoconized coca leaf extract. Chemically though, it's about as close as you can get without it, and the real deal should be fairly similar.
I don't know why the captions
The
are lagging
recipe
behind
is
now, but I can't really fix that,
45.8
so...
milliliters lemon, 36.5 milliliters lime, 1.2 milliliters orange, 8 milliliters tea tree, 4.5 milliliters cassia cinnamon, 2.7 milliliters nutmeg, 0.7 milliliters coriander, and 0.6 milliliters fenchel. And optimally, you'd let this mixture age for a day or two before continuing. Art of Drink has an excellent video explaining why, and even the original Pemberton version of Coca-Cola includes this aging step. In the end,
Well, I don't know what other aging voodoo magic is happening based on what people are saying, other people are saying, but I do imagine it's probably just because if you let it sit for a day, then that goes ahead and means the chemicals all get to react with each other and form some additional things in the mix. Ooh, delicious extra flavors.
you'll be rewarded with about 100 milliliters of flavor oil, which is enough for over 5,000 liters of soda, or about as much as your mom drinks in a day.
Damn.
To make the 7X solution, simply dilute 20 milliliters of the flavor oil to a volume of 1 liter using food-grade alcohol. And before anyone gets worried, the amount of alcohol being added to the final soda is 5 times less than what you get from a non-alcoholic beer, and far too little to taste or make this drink intoxicating. Other flavor extracts like vanilla
Wow,
or
I
almond
didn't
use
think the
ethanol as a
math would,
solvent. This
work
is
out
no
that well.
different. Still, if alcohol is an issue, you can emulsify the oil into water with the help of gum arabic. Check out Glenn and Friends Cooking to see how he does this with his cola. Anyway, next, we'll need to make a secondary water-based solution containing the other ingredients, aside from sugar and carbonated water. Into roughly 200 milliliters of hot water, measure out 10 milliliters of 5% vinegar, 9.65 grams of caffeine, 175 grams of glycerin, 45 milliliters of 85% phosphoric acid, 8 grams of wine tannins, 10 milliliters of vanilla extract, and 320 milliliters of Shank's caramel color. In case you're wondering, the glycerin is being added for texture and mouthfeel. Without it, the drink tends to feel a bit thinner and more like diet soda.
Interesting.
Also, if using vanilla extract feels imprecise, you can alternatively mix up a solution containing 9.5 grams per liter of vanillin and use 1 milliliter of that. Given the fairly limited impact vanilla seems to have, though, you
the
probably
vanilla
wouldn't
extract
notice a
could
major
change
difference.
from brand to brand.
Give each ingredient time to fully incorporate before adding the next. And once everything is
Going to the
dissolved,
trouble of buying
dilute the
essential
mixture to a
oils,
final
might as well
volume
buy
of
pure
1 liter
vanillin.
using water.
Vanillin.
Now, let's make some Coca-Cola. For this demo, I'll be making 1 liter, just so scaling up or down is a bit easier. Into a glass dish, add 104 grams of sugar, and just enough water to dissolve everything. I know I said 110 grams of sugar per liter of soda at the beginning of the video, but here's the deal. That's for a mixture of fructose and glucose, like you'd find in corn syrup. If we add 110 grams of sucrose, or cane sugar, the phosphoric acid will cause it to react with the water and form nearly 116 grams of those simpler sugars. That would throw off the sweetness of the drink, so we use less sugar to compensate.
I see. You end
Anyway,
up getting
next,
mass from
we
the
add our flavor
phosphoric
solutions to
acid.
the syrup. 10 milliliters of the water-based solution, and 1 milliliter
And
of
the
the
water.
alcohol-based 7X solution.
Let's just use
You
corn
might need
syrup
a few
straight
extra
up.
drops of the 7X solution. It really depends on your taste. As soon as everything is combined, microwave or otherwise heat the mixture until nearly boiling, and cover to prevent the more volatile flavors from escaping. Heating like this helps the phosphoric acid break down compounds like limonene and citral, and it also accelerates that sugar hydrolysis reaction we just talked about. so it's a fairly crucial step. Once fully cooled, dilute the syrup to a volume of 1 liter with cold carbonated water. This can either be bought or made yourself using a soda stream. Just don't attempt to carbonate the fully mixed soda on the machine. It tends to produce a lot of foam, which can lead to bacterial growth if you're not careful.
And leaks, which are a pain in the ass.
This is our finished Coca-Cola. You can drink it directly, but if you want the most accurate version of the final flavor, allow the soda to rest for a day or so in the fridge. And again, while the flavor is as close as I could get to Coke after a year of trying, and certainly closer than any other clone I've tasted, there is still room for perfection. So if you have the ingredients, feel free to experiment. And for future reference,
so if
I'll
you
have
have
the
coca
most up-to-date version of
leaves,
the recipe in the video description. Of course, I could go on and on about how I think my cola tastes, but what do other people think? Is this a convincing replica, or just
Vocalic
another
acid.
Pemberton knockoff?
True.
Well, I said.
Well, that would be I'm guaranteed that would be the name someone would give if they found a specific acid within coca leaves. They would call it cocalic acid because chemists are not creative with their names. I mean, for fuck's sake, we already saw something called limonene coming from lemons and limes.
Several blind and non-blind taste tests, and people actually had trouble telling it apart from real Coke.
This is regular Coke. See, I can't even tell. Even though I know already, I can't even tell.
9.5 out of 10.
9.5 out of 10. That's pretty good.
That tastes pretty close. Like, I may not be able to tell if these were side by side with the original taste.
I know that is definitely, Coke or a Coke product. If you said it was vanilla Coke or something like that, I'd be like, yeah, maybe that's definitely Coke.
I think this is more similar to this bottle than this is to that bottle, which is crazy to think about now that I said that out loud.
Yeah, that's a Coke product. I wasn't expecting it to taste so much like Coke. Oh my gosh.
From the bootleg Coke bottling plant.
Yeah, that's good. I mean, like, if you sold this on the shelves, I'd buy it.
Regular Coke drinkers were better picking mine out from the mix, but the general consensus was that Lab Cola could be mistaken for Coke, and not other colas like Pepsi. When tasted on its own, without Coca-Cola as a direct reference, people overwhelmingly thought it was the real deal, unlike the Pemberton recipe, Open Cola, and other clones I had them try.
Yeah, that's not Coke. Oh.
No, that's not Coke. No, that's not even, it's a cola, but, that's not Coke. That is just straight flour.
It's very cinnamony to me. That's almost pure cinnamon.
Really shows how far those tannins and herbal notes go.
But it's definitely not Coke.
Alright, I think that's finally it. 2025 is coming to a close, and it has been an insane year for this channel. Thanks to everyone's support, I was able to take on crazy projects.
You don't know
like
how much
pouring
more
gas
crazy
at
it was
home,
just about to get with
preparing
this
oleum
video.
bond solution, and putting a 360 camera probe in front of a tornado. Stay tuned for that adventure. 2026 is shaping up to be another great year for LabCoatz, although there are a few changes on the way. If all goes well, I'll be graduating in May with my bachelor's degree in chemical engineering.
Yippee!
And moving to a new location where I'll be doing an internship and hopefully getting a full-time job. It's hard to say how many videos I'll be putting out at that time, but rest assured if there is a little break in there, it's not going to be permanent, and I will be coming back.
I will say, you can very much tell just from the quality of the videos that he puts out, the quality of his science. This is one of those people who just genuinely enjoys doing this kind of chemistry work for fun. This is this flat out is their for fun, I'm gonna go do this for just dicking around kind of hobby. It's not like I know the guy personally, but that's one of those things that's I admire it because I can't be that way. I like doing home chemistry every once in a while, but I haven't done it in several years because I'm more interested in gaming and streaming. So whoopsie, but still, it's really cool.
Starting projects, I have several chemistry-themed ones planned out,
Ooh, crystallization.
including making taurine for my own energy drink, and finally finishing my work with super stenches by taking on tellurium.
Oh god,
I also
make
bought over $1,000 worth
organotellurides.
of capacitors to build a plasma gun. And for storm chasing, I got this high-speed drone to film tornadoes up close and personal. Kind of like the Otis project, but cheaper.
Yeah, provided
Now
you're gonna
I
get
just need a
your fucking
license.
drone back.
If you'd like to help support me and my channel, feel free to donate, join my Patreon, or become a channel member. Or pick yourself up a sample of the Lab Cola flavor stuff. As always, a big thanks goes out to all the existing LabCoatz Patreon supporters and
I think it'd be very interesting if he actually tried selling Coca-Cola or his Lab Cola at some point. It's not like he hasn't done giveaways or things like that before. Current recipe, same as video, but using different amounts of some of the other stuff. Using this other caramel color. Shanks no longer seems to be available. Damn, they got pulled. Big Coke got to them. I'm just curious what some of the comments have to say, given this is LabCoatz's like strongest video so far. Sorry for your car accident tomorrow. Seen people disappear for less. Oh. Releasing the Coke files. Company making the knockoffs are going to use your video for improvements. Nice. Nice. Well, hey, hope you're not sick of hearing about Coca-Cola, because before I think video about just a week ago, I got a video from Reactions, which is actually an official American Chemical Society channel, I'm pretty sure. Yeah, a production of the American Chemical Society. So they actually make really cool, informative videos on, just fandom, various chemistry topics. Usually stick around the more simple regime. But honestly, given the fact that we just had a video talking about replicating Coca-Cola, and now we have whatever this is going to be about Coca-Cola, I'd love to see these two things back to back. And boy, wouldn't it be funny if this was literally something that this person's about to say, like, oh, whatever this revolution for Coca-Cola happened, it was in, like, late January. It's like, did the Coca-Cola CEOs really have, like, an emergency pull if someone discovers the fucking formula button and just do this? I doubt it, considering this guy doesn't have coca leaves, but still. It's, I have no idea what to expect, and I'm interested.
In my last video about Mexican Coke, I made an incredibly bold claim. Mexican Coke is a lie. This bottle that I tested at the beginning of the video contained, from what I can tell, 0 sucrose in it. And that led me here, which led me here, and I discovered something that Coke is doing that they haven't told anyone.
Oh no.
This is the American Coke?
Correct.
Okay. That's not what I expected to see. Coke is not telling anyone about this. They're keeping it as secret as the federal government will let them.
It doesn't even say anywhere. It says,
in my first video, I tested Mexican
we're doing
Coke
an investigation
with a
of
blood
ingredients.
glucose meter and a more than century-old chemical reaction. And based on those results, I claimed that Mexican Coke has no actual sucrose, also known as sugar, in the bottle, despite saying cane sugar right here on the label. That was an
added, reacts with the phosphoric acid.
I never actually measured the sucrose. I only measured glucose. So, 2 chemistry professors decided to call me on it. This is Jeb and John. They're both professors at Shippensburg University, and what they did is they hired an undergrad, this is Rebecca, to attempt to replicate my results. She used this machine. It's a high-performance liquid chromatograph. Everyone in chemistry just
Okay, I will say, maybe to some of you it seems like, wow, that's a that's a hard task to put on, like, an undergrad to, like, try to replicate the results of this one guy's video and, like, try to analyze if that's, like, the proper Coke and what have you. What stands out to me is actually, like, no, this is exactly, like, the perfect undergrad project. Not only is it, like, here's a set of instructions you can just watch a video and basically follow, but you have, like, hired, like, grade equipment on you. But then there's also just the factor of, like, no research grant would ever go to fucking pay this. But, you know, an undergraduate research grant from, like, the school's, like, funds to just kind of encourage science amongst the undergrads. Yeah, you know, that might fund things. We could maybe spare $3,000 or $6,000 for a summer stipend for this kid to come on in and do some science and learn how to operate some instruments. It's not groundbreaking paper making science, but, you know, it's good practice for them.
calls it an HPLC. Rebecca bought several samples each of Mexican and American Coke. She sonicated them to get rid of all the carbonation, and then she filtered them, and then she ran them on the HPLC. The data this machine spits out looks like this. It's called a chromatogram. The x-axis is time, and the y-axis is millivolts, but you can just think of it as concentration. Now, each of these peaks that you're seeing represents a single chemical. And you know which peak is which because
we already
before you
talked
ran
about
your
how
actual
that
samples,
isn't quite
you
it.
ran pure compounds, and you saw how long each of those took to elute. Elute. That's a good word. And the area under each peak is proportional to the amount of each of those chemicals.
With the same amount of sucrose, glucose, and fructose, the sucrose peak would be visibly larger than a glucose peak, and the glucose peak would be visibly larger than the fructose peak.
Now, in my creepy basement, the best I could do was to sort of semi-quantitatively measure only glucose. But this HPLC can measure all three sugars at the same time with much higher precision and accuracy. Now, look at these two chromatograms. One of them is American Coke, and the other is Mexican Coke. And if you want to pause the video here and guess which is which, please do that right now, because I'm about to tell you that the one with the larger fructose peak is the American Coke, which makes sense because it's sweetened with high fructose corn syrup. In other words, corn syrup that has more fructose than glucose, so you would expect a larger fructose peak.
Black line is Mexican Coke, and pink line is American Coke.
Yes.
Nailed it. Now, this is the Mexican Coke, and as you can see, the fructose and glucose peaks are basically equal in size, more or less, because all the sugar in the Mexican Coke started out as sucrose, which is 1 unit of glucose bonded to 1 unit of fructose, so you get equal amounts of fructose and glucose. The bottles of Mexican Coke that Rebecca tested had on average 2.8 grams per liter of sucrose left in them. So in these bottles of Mexican Coke, 97% of the cane sugar had been destroyed by the acid. In other words, in my first video, I was 97% right.
Well, I mean, no, because if the label says that cane sugar was added and that's sucrose, then if it's getting, if it's reacting and being with the phosphoric acid and being ripped apart by the phosphoric acid into glucose and fructose, it's not wrong. It's just saying that the things that they added individually form different compounds. Like, that's not wrong for them to label that on their bottle. I'm not going out and defending the $75 trillion company, but, like, you know, it's not incorrect.
Which I'll take. I'll take that. The next interesting question is, how long does it take for 97% of the sucrose to disappear? And does that mean that any bottle of Mexican Coke you buy will have no sucrose in it? Now, to really answer this question, you need a bottle of Mexican Coke in which the reaction hasn't started yet.
You need because the phosphoric acid will
if Mexican
very,
Coke
very,
really and
very
truly
quickly
is made
react.
in Mexico, then it would take at least a few days
Acid
to get
is
up here
just
to
a
Pennsylvania,
quick reactor.
by which time it might be too late to get the measurements you need.
You
So
went
the
to
team
Ohio
found
first.
a local soda company, Reading Soda Works, that was about an hour away, and they bought a bottle of freshly bottled sarsaparilla soda that was sweetened with cane sugar, and they ran it on the HPLC. And they were doing this as a baseline, basically to figure out how much sucrose had been hydrolyzed. And they found that basically none of it had. None of it. So they tested the pH of the sarsaparilla soda, and they found that it was about 4.6.
Oh,
That is
okay.
1.85
So it's
units
slower than I
higher
thought.
than Mexican Coke, which is way down at 2.75. So that means that Mexican Coke has
Is
almost
much more acidic. Okay, that makes sense too.
times more acid than the sarsaparilla
So it
soda.
might include vinegar.
Is that right? I think that's right, because you do 10 to the 4.6 or 10 to the minus 4.6 or something. Sorry, 71 times
Logs,
more
how do they
acid
work?
than the sarsaparilla soda. Okay, it's not 100. So then the team did something that I think is super clever. They took the sarsaparilla soda and they added hydrochloric acid to it to get it down to a pH of 2.75. In other words, matching the pH of the Mexican Coke. And then they split it up into 3 batches, and they stored it at 3 different temperatures. 3 Celsius, which is about the temperature of your fridge, 22 Celsius, which is roughly room temperature, and 39 Celsius, the temperature of a hot summer day. And they followed all
Let's
3
leave it out to
batches
stale in a
for 3
fucking
weeks.
warm oven.
And after just 14 days at 39 Celsius, all the sucrose was gone. All of it. Even at room temperature, after just 3 weeks, that's an additional 1 week, almost half the sucrose had hydrolyzed. This is not the shocking thing that Coke is doing, but it did make me wonder. If the Mexican Coke you buy at the store contains a 50-50 mixture of fructose and glucose, and the American Coke you buy at the store contains those same two sugars but in a slightly different proportion, 55% and 42%, is this very subtle difference really what people are tasting when they distinguish between American and Mexican Coke? This was a big question in my first video.
Maybe.
Now, I had a hunch that the answer was no. So, I brought a sample of pure high fructose corn syrup to Jeb and John's lab, and we ran it. Look at this chromatogram. All right, so these are the fructose and glucose peaks. They are as you'd expect.
Yep.
The fructose peak is higher. And this right here is a little tiny sucrose peak. But what is this? This small peak at 5.825 minutes.
That's
now,
the cornoline.
We went back and looked
I
carefully
don't
at the
fucking know,
chromatograms
but
of
it's probably
Mexican
something
Coke
due to corn.
and American Coke. And we confirmed that, yeah, this tiny little peak is present in American Coke, but not in Mexican Coke.
Wow.
So my interpretation of this is that there is something, probably a sugar, in American Coke that is not present in Mexican Coke.
Yeah. Yeah. Now the amount isn't large.
Right. It's small.
But it's detectable.
But like
this is detectable.
This is at a concentration that is well above taste thresholds. Like
probably.
You depending on what this is and what the actual taste threshold.
Right.
You could probably taste this.
Possibly.
Possibly. Back in 2014, during the initial Mexican Coke wars, a group of scientists from the International Society of Beverage Technologists published this paper. Now, this paper contains a chromatogram of a soft drink sweetened with high fructose corn syrup. And there are actually multiple peaks that come off before
multiple
the
little
glucose,
ones.
which they identify as maltose, maltotriose, and maltotetraose. Now, those are fancy names. All they are is 2, 3, and 4 glucose subunits joined together, respectively. Now, it's possible that this peak right here that we found in our high fructose corn syrup is maltose, or maltotetraose, or even a mixture of all of these glucose oligomers, or some other higher order sugar. In my last video about Coke, I glibly dismissed the idea that anyone could taste the difference between sugars. But what about everybody who claims they can specifically taste the difference between cane sugar and high fructose corn syrup in a soda? Those people are just wrong. Yeah, turns out I might be wrong.
Really? The guy who is thinking
here's
that
the
you
deal.
can't label your thing with
we are gonna run
sucrose
a
if
taste
it
test in this video
isn't
that will
present.
help answer that
Okay.
question. A taste test that it would not have been possible for anyone to run before now.
Anyone.
The night before we got to Shippensburg, Jeb found this bottle in a store in Mechanicsburg, Pennsylvania. This is a holiday edition American Coke, except
Holiday
it's
edition?
made with cane sugar. This is the Holy Grail. It's the thing that started the Coke Wars. It's American Coke with cane sugar. And no
Probably
other
came from the
differences. It's got
same
Mexican
goddamn
Coke
bottling
with this
plant in
double
Mexico.
sodium and who knows whatever else. Obviously, Jeb bought a couple bottles, and we immediately threw it on the HPLC. Now, we were all expecting to see basically the same
Just a different
chromatogram
label.
as Mexican Coke. Complete inversion, complete hydrolysis of the sucrose. But that is not what we saw. Look at this massive sucrose peak. There is still roughly 64 grams per liter of the original cane
Wow.
sugar left in this bottle.
I'll leave it sitting out for a
now
couple of
we have
days.
to rewrite this whole video.
From a sugar standpoint, this Coke is nothing like Mexican Coke.
So either this is not very old or it was kept at a very cold temperature.
Yeah.
Probably
I
that,
can
especially
actually-
considering
I
you
can
got it
actually
within
do
the same
that.
state.
If you want me to.
Yeah, let's do the math.
So base. Oh, I'll be back.
Okay.
Yeah, I'll be back. Yeah.
That's the best kind of math when somebody else does it for
When
you.
he says based and walks away, yeah.
What I get based off the idea that it was stored at room temperature the whole entire time.
Yeah.
Was that it was only bottled 21 days ago.
They could market this as different. Yeah. Because if I would have consumed this versus a regular American Coke, I would have had a different sugar, like, profile experience in my, you know what I mean?
Coke did something very special here. They gave us a soda that has the low pH that we've come to expect from Coke, gives us the bite and
They
the
just
burn,
got it out
but
of the
also
factory
has
faster.
Most of the intact cane
over to
sugar
the shelf.
left in the bottle. It's mostly a cane sugar soda. Coke has not done this before. This is an achievement. And who did they tell about this achievement? No one! They didn't tell anyone.
It doesn't even say anywhere. It says, yeah, it says you have to look to find that it's cane sugar. That's why.
Look, nowhere on this bottle does it say cane sugar or real sugar or any of the other marketing terms
says it
that
right
other
there.
companies fall all over themselves to tell you. The only place on the entire packaging where you will see cane sugar is in the ingredients label,
Yeah,
which
where
Coke is required
normally
by law
goes
to disclose.
where it normally
this
goes.
is the Coke that allows us to run a taste test that we have never been able to run before, which is American Coke with cane sugar versus American Coke with high fructose corn syrup.
But you also need to run the experiment of
was
American
also
Coke
struggling
that's
to
been
figure
left
out
out in the
what
sun
is
for like
Coke
a
up to
fucking
here.
month, so that
Have
way
they
it
lost
has all the shit
their
broken
minds?
down, and maybe it
Do they know
tastes
something
really
we don't
similar
know?
to the normal American
I don't,
Coke.
and I don't
Or
know.
maybe it doesn't. And if it does taste really similar to it, and no one could tell the damn difference, then your original hypothesis of, oh, no one could taste the difference between like 7% of the different sucrose and glucose percentages, then that would be correct. If they can still taste the difference, then your original hypothesis is wrong. As you're testing it, your shit doesn't make any sense. This experiment does not make sense. You're not actually fucking controlling for things. You need to have one that like is not broken down into the two sugars. You need to have one that is broken down with time into the two sugars. Then you can actually test a proper matrix and make comparisons that actually make sense between the samples that normally exist, being normal American Coke with high fructose corn syrup and Mexican Coke that does not have high fructose corn syrup and uses cane sugar. This experiment doesn't make sense, and it's bothering me. This is something that if I presented this to my analytical chemistry professor back when I was an undergrad, they would have been like, you're not testing your variables right. Come back again next week, C-. And it'd be like, oh, okay, but if I was a professional chemist and I fucked this up in my educational video for the American Chemical Society, then it would just be fine.
Anything about marketing, economics, companies, or really capitalism. So I found some people who know more about economics than I do. Let's go. I broke into NPR headquarters and tracked down two of the hosts of Planet Money. Could I have you guys close your eyes?
Sure.
We did some taste tests. Taste all three.
Okay.
Think about
You need a
whether or
fourth.
not
You need
one
a
of them is
fourth.
different from the other two, and
Okay.
if so, which one?
Okay. I think number 3 is different.
Just saying
Vote
triangle
locked.
tests?
It's maybe a little less sweet.
I
number
agree.
3. No, maybe
Before
one.
this,
One.
George.
I think one is less.
Oh my god. Oh my god. Jeff's-
maybe 1 and 2 are less sweet, and 3 is sweeter.
So
Wow.
okay, 3 is sweeter.
Jeff's now named all of them.
And they disabused me of some of my conspiratorial thinking.
What better marketing than the President of the United States saying, go buy some cane sugar Coke?
Yeah. And that feels a lot less conspiracy theory and more like what a company would try and do if they were on their game.
A rapacious profit maximizing company that
Indeed.
wants to sell as much sugar water as possible.
Yes.
Oh, sugar water is
U.S.
tasty.
cane sugar prices are just artificially high. You could always count on cane sugar being more expensive to some degree. And so high fructose corn syrup could sort of always sneak in under.
The amount of sugar in a can of Coke,
Yeah.
if it's high fructose corn syrup, it costs wholesale maybe 4 cents. You're looking at 4 cents of sugar.
Wow, okay, that's lower than I expected. Oh
in a
my
can.
gosh. Yeah.
And if that were cane sugar
Yeah.
at the current spot price, that would be 4.7 cents. And then multiplied by however many bajillion cans that Coke sells.
Yeah.
Like, it makes a difference.
Yeah. And then I
Feel
wanted
the
to see
trillion-dollar
if they could
company
taste
might have
the
to spend
difference
another $1
between
million
cane sugar
on cane
and high
sugar.
fructose corn
My
syrup
goodness.
in American Coke.
Look, oh, bro.
So now we are tasting Coca-Cola products.
I think they're all the same, George.
Number 1 is sweeter to me.
Okay. Well, okay. He had a 1 in 3 chance of getting it right.
No, you have to test Kenny again right now and see if he can replicate.
Okay.
Absolutely not. I refuse.
So we tested Kenny again.
Oh no, I think this was the cane sugar.
Nailed it. You're right.
What?
You nailed it.
Kenny, are you a super taster?
Maybe.
And we tested Kenny again.
I think it's this one.
So you're actually wrong. It was the middle one.
No.
Yeah.
I'm not a super.
No.
I know.
Well, I mean, the guy's
I don't think
tongue
so.
has
I
been
think it's
coated by
really hard to tell the
Coca-Cola.
difference.
And yes, obviously Jeff and Kenny are very far from making a statistically significant sample, but this is what I think of these very limited results. Jeff and I got it wrong. I think the one to my furthest left is cane sugar and the other two are high fructose corn syrup.
No.
Kenny tried it 3 times and got it right twice.
Should I quit this job and go become a sommelier?
So maybe there are some
No, a Coke
people
sommelier.
whose taste buds really can detect this difference. And maybe all of them commented on my last video.
Yeah, so if my outrage wasn't evident, I maybe didn't like that video so much. It was less interesting than the fucking amateur guy on YouTube who I always watch, and this is like backed by real American Chemistry Society money. Yeah, like that was not the rigorous test that I was hoping for. That didn't actually talk about. It didn't make a fair comparison between any of these. I guess it kind of makes the comparison of like, well, you know, you have the one that apparently has the cane sugar, but it's like you're comparing the one that still has the sucrose peak when people are usually talking about how they can definitely, totally, really, definitely actually claim a difference in flavor between the Mexican Coke that has the cane sugar, but when you sample it, the sucrose is all broken down because it's been sitting in a warehouse or a fucking truck for like, you know, a month and a half, versus American normal Coke, where it has the high fructose corn syrup, and so has a slightly different, uneven ratio of the two as separate sugars. Meanwhile, you just tested this one against one that still has sucrose in it, and it's like, that doesn't prove your original point at all. It's a separate thing entirely. People can definitely taste the difference between a large amount of sucrose and almost no fructose or glucose in there, versus no sucrose and just fructose glucose. Like, the big amount of sucrose will make the difference there. But like, you're not. It's not comparing against your original hypothesis. This doesn't prove shit. I need a follow-up video. Reactions if you see this. Please do the thing that I'm asking for. I know you can do better than this. All right. So, given that I have a day off tomorrow, I am going to do the last video in the 4 that are in the thumbnail because I don't want to wait another month to watch this video. We're going back to Old Reliable. We're going to the United States Chemical Safety Board for an explosion video. Hell yeah. That'll wake everybody up at the end of this long 2-hour session here. So I think based on the title, we're going to get a video related to a dust explosion. So combustible dust accidents are very common in industry. Well, I won't say very common. They don't happen every day, but they are one of the more common causes for explosion, and it's basically just poor hygiene that usually causes it, where a factory floor is just coated with some kind of combustible dust. Usually that is a very fine metal powder that just hasn't been cleaned over years, and it just gets all shaken up one day, gets into the air, a spark ignites things, and the resulting oxidation reaction runs away and causes a big explosion fireball. Or you could have an organic, such as the one that I showed earlier from this channel many months ago on a sugar dust explosion. Yeah, thankfully this is something I don't have to worry about in my safety job because while the labs are a mess, they at least mostly contain the chemical mess to a fume hood. So the most a fume hood might explode from dust buildup. But thankfully no one seems to have done something that stupid in my time here. Fingers crossed it doesn't, happen while I still work at this university, but still, you can see what happens when it scales up to a whole ass factory.
May 31st, 2017. The Didion Milling Dry Corn Mill in Cambria.
Ooh, more corn. Shit, we're on theme too.
After an initial combustible dust explosion occurred within milling equipment, fires propagated inside of the process piping to other areas of the facility. Meanwhile, outside of the process,
the building is turning orange.
Spread throughout the mill buildings, causing significant damage that ultimately destroyed the facility. 5 people died and 14 were injured.
The hazards of combustible dust are well known, and combustible dust explosions and fires can be deadly and incredibly destructive. The terrible tragedy at Didion was made even worse due to poor hazard recognition, inadequate fugitive dust management, and a lack of dust hazard analyses. Our investigation also determined that Didion had a poor safety culture and ineffective leadership on safety issues. These factors led to a catastrophic incident that could have been prevented.
At least that's a pretty good idea of who should replace, the narrator for the USCSB once he gets too old. Because I'm pretty sure the current narrator is like some 70-plus-year-old Irish guy, and you know, eventually that's going to be too old, and we might need to get J.K. Simmons into the role. He could probably do something pretty similar. He definitely has that kind of authoritative voice.
Didion Milling is an agricultural processing company with several facilities based in Wisconsin. At Didion's dry corn mill, located in Cambria, Wisconsin, corn kernels were ground into smaller components for use in a variety of corn-based products. The process of grinding
how little that narrows it down? Everything in America is
corn-based products and dust. Both the product and dust can be combustible.
They've been really using this nondescript 3D gray tile space a lot. I mean, I guess it's better than just a blank white void for them to be doing physics simulations in, but it's starting to feel like a you know, a little bit of a cheap asset. You know, they could at least do it in like some kind of empty factory floor. Anyway,
can present flash fire.
The animation does look really good. I can't deny that.
Hazards when dispersed in sufficient concentrations and ignited in air. Also, when product or dust accumulates in process equipment, it may, under certain circumstances,
hey, nobody bothered to clean
begin
it.
to smolder, leading to what is called a smoldering nest. Smoldering nests can rapidly transition to a flash fire or explosion if the smoldering material is disturbed.
Kind of like setting a leaf pile on fire. Fire could still be inside.
And dust present serious hazards that must be understood and carefully managed. On May 31st, 2017, shortly after 10:30 p.m., multiple employees at the Didion Mill facility noticed an unusual smell or saw smoke. Several employees searched the facility, trying to pinpoint the source of the smoke.
Where's Jack? He
They
must be smoking a
determined that it was
cigarette
likely
again.
coming from the first floor of one of the mill's buildings, known as B Mill, but could not pinpoint the precise location. The CSB determined that the smoke was likely coming from a smoldering nest located inside the corn grinding process. 2 employees on the first floor of B Mill.
And I guess good point. How does one of those smoldering nests starts? I mean, you know, they kind of said it's the idea of the accumulation of dust that isn't cleaned over time, and just basically like you get one happenstance reaction that happens underneath the corn dust. You get a spark that maybe just comes off of some equipment, or just, you know, 2 pieces of metal knocked next to each other that one day, and just, well, that created enough heat. And once you get enough heat, you start burning things, and once you start burning things, you burn more things, and now you have smoke and burning corn.
Had been searching for the source of the smoke for about 20 minutes when they heard a huge boom. An explosion had occurred within the process equipment. Immediately thereafter, flames erupted from piping connected to one of the 2 gap mills on the first floor.
Well, that's not
At
good.
the same time, the employees saw dust misting down from overhead piping.
Corn dust everywhere.
Recognizing that the
No
overhead
one's cleaned
dust
this
cloud
fucking
was
place.
likely to ignite, both employees raced to escape. One of the employees made an evacuation announcement on
Yeah.
one radio channel.
At least they got the fuck out of
Did not have
Dodge.
time to make the announcement on all radio channels. Before he could alert others to the danger, a larger secondary explosion occurred on the first floor.
Yeah,
The
it's
destruction
crazy.
at Didion was now set on 2 tracks.
Like, again, literally, this is just corn dust. This is not a proper explosive or anything like that. Hey, Chris, welcome. Who's the narrator? Morgan Freeman. All right, first we have Omni-Man, J.K. Simmons, and now we have Morgan Freeman as a possible narrator. We'll tell you what, if they have the credits up and it's obvious, we'll look for the name at the end here. But I know that the CSB narrator is a very iconic voice. This will be one that's hard to replace once he gets too old.
Inside of the process, a pressure wave from the initial explosion dispersed
Kicks up the
accumulated
corn.
product and dust. This provided fuel
Oh, an explosion
for a
is
flame
self-propagating.
that propagated inside piping and equipment within B Mill from the first floor to the floors overhead. The flame front ultimately propagated to a large dust collector called the dry grit filter, which
Yeah,
was
that dust
located
collector is
outside of the building.
only so useful. You
Once
gotta clean the
fire
rest of the
reached
building,
the dry
too.
grit filter, the equipment over-pressurized and released a fireball, which engulfed one of the evacuating employees.
It looks like he got away.
The flame front was able to propagate inside the process.
Bad hitbox on that flame.
Equipment
You know.
into the mill's other buildings. Outside of the process, the fire from the initial explosion combined with combustible dust from disconnected process lines and fugitive dust dislodged from overhead surfaces, and began a series of secondary explosions throughout the facility.
Again, just corn dust.
Caused multiple buildings to collapse,
Just corn dust.
ultimately destroyed.
You need to clean up after yourselves in an industrial
19
setting.
employees were working at the dry corn mill at the time.
Not even just yourselves, just the company
All of
needs to
those
clean up after
employees
itself.
were injured.
Can't skip on this.
Fatally.
The U.S. Chemical Safety Board launched an investigation into the incident at Didion Milling and found 13 safety issues. Among these were process hazard recognition.
Okay, here's my... So how many safety issues did you just say? It's my time to guess as a safety professional.
13 safety issues.
13 safety
Among these
issues.
were
Okay, I don't know if I can guess 13 safety issues. Goodness. All right, that's a lot to have to go through. All right, so we're starting with whatever this process hazard recognition is, which I'm that's so general I can't even really discuss what that necessarily means. But I guess a couple of things I could identify. So, one, just lack of cleaning, regular cleaning upkeep. Two, lack of alarms or like lack of fire alarms. Three, you have like also a lack of like secondary like fail safes. There's no like often what is it usually called? A flame arrestor. Flame arrestors are usually in systems where a fire could reasonably be anticipated, and they will stop the propagation of a fire from going too far back into like a fuel source. You'll usually see this on like a gas line or something like that, where if the gas gets lit on fire outside, the tank will have a flame arrestor, which is just like a mesh piece of metal somewhere along the line that would cause the flames to dissipate because physics reasons, can't get too deep into it. So okay, that's like three things. Another one is like did I already say lack of emergency something? It seems like there was lack of like say sprinkling maybe to put out the fires. You also had like lack of PPE, though I mean I guess it's just corn, they weren't expecting it, but you know, still it's combustible. I don't remember if I already said lack of emergency, like, warning system. Like, there wasn't a formal emergency warning system in place, and there wasn't able to warn everybody. So I don't know if I already said that. I'm a little tired, but you know that's certainly contributing to the disaster and why people died. What else? I don't know. It's hard to kind of come up with 13 different reasons why something went this badly. But I mean, it's all just encompassed in like really poor household maintenance and really poor planning for this kind of emergency situation, which is totally anticipable. And I guess that's a word. And I'm calling it one now. You know what they say, butterfly effect? Sort of, I guess. Yeah, I mean, that's not how I would use the idiom, but it is kind of like a, you know, a small thing of one, you know, a couple pieces of corn accidentally getting too hot and starting to catch fire, having a biochemical reaction. That could have been that too. Fermentation creates a lot of heat. There could have just been a warm spot of fermentation somewhere, and eventually that could have caused the, you know, the smoke to go up. But anyways, let's see what 13 issues could possibly be.
Hazard recognition, dust hazard analyses, fugitive dust management,
dust management,
process safety leadership.
Okay, I guess the dust hazard analysis is part of it. Maybe they just didn't understand that this could even be a hazard. So I guess that's something to think of.
And regulatory coverage of combustible dust.
One safety issue is process hazard recognition. During its investigation, the CSB found that many of Didion's ground corn products were of a small enough particle size to themselves be combustible dusts. In fact, every material that the CSB tested, including final products, as well as other materials found in Didion's processes, qualified as combustible dust.
Yeah, you know, we got this corn meat. We got this bomb at the cornmeal factory. It's a bomb.
Despite previous warnings from external inspections, the CSB found no evidence that Didion understood or recognized the hazards of combustible dust. As a result, the company did not recognize that many of its products and process streams presented combustible dust hazards.
Yeah, okay.
For example,
yeah,
in addition to other design flaws found in the mill, the company did not recognize that connecting numerous pieces of equipment
literally just thought it's
with the
corn
same
dust. How could it blow
collection
up?
System could lead to a flame propagating throughout
Yeah,
the facility.
why not just connect everything?
Had
It's just
Didion
corn.
limited the process equipment interconnections at the mill facility, the initial dust explosion could not have propagated throughout the process equipment so easily. Instead, a flame front reached the dry grit filter and then propagated to other previously uninvolved parts of Didion's processes. This allowed damage to spread to processes and buildings that otherwise likely would not have been involved in the incident.
A second safety issue found by the CSB concerns dust hazard analysis.
Corn, there's corn everywhere.
Dust hazard analyses, or DHAs, are assessments of processes to determine potential combustible dust hazards, and are outlined by guidance from the National Fire Protection Association.
It is kind of still amazing though that they may not have thought that they're on their own that corn was like combustible dust like that, but there's plenty of documented cases of combustible dust fires in industry, in the food industry too, from sugar. Like, you know, you hope somebody would have tipped them off, but guess
Didion
not.
had not performed any analyses of the grain handling processes for potential fire and explosion hazards. And the CSB found that the NFPA guidance did not cover all equipment that could have the potential for combustible dust hazards.
Even if Didion had performed a timely DHA, the company could have still potentially missed the fire and explosion hazards in the equipment where the smoldering nest and first explosion likely occurred. Therefore, the CSB believes the NFPA guidance must be improved.
As a result, the CSB made a recommendation to the National Fire Protection Association to update its guidance to unify the requirements.
Best news is this
performing
agency
dust
might
hazard
actually change,
analyses to
unlike
remove
OSHA, who hasn't
equipment
really changed anything
exceptions
since
and
1980.
require the assessment of all processes. In response, the NFPA has published
Wow,
a new
look at that.
comprehensive combustible dust standard, NFPA 660,
And most
that
people
addresses
actually follow
this
the NFPA.
recommendation. A third safety issue identified by
Good
the
job,
CSB
NFPA.
is fugitive dust management. Fugitive dust presents a serious safety hazard because it can accumulate within facilities and provide fuel for secondary explosions
Fugitive dust, it
that
runs
an
from the
initial
cops.
fire or explosion can shake loose and ignite. At Didion, the large secondary explosions that occurred outside of the process and accounted for significant building damage and employee injuries were at least partly fueled by fugitive dust. This is why housekeeping or cleaning practices meant to manage fugitive dust are critical. They minimize
Yup, there's the
fuel
housekeeping I keep
available
complaining
for
about.
secondary explosions. To be effective, housekeeping must be done consistently and leave no unmonitored areas for dust to accumulate.
You have to turn over every
But the
single
CSB found
stone
that
and
at
pipe.
Didion, the control
hopper.
of fugitive dust fell under the site's master sanitation program.
Oh, God.
The sanitation program, however, was based on food safety standards, intended to reduce hazards like pathogens and contaminants.
Yeah, you can just have the fucking corn dust lying around as long as it's not within the actual path of the food production. It's totally fine. There's no issues there. Just work in a fucking environment that's entirely coated in corn dust. There's no issues here.
It was not based on workplace standards meant to minimize process hazards.
Whatever the
like
fuck
those
is in that,
presented
dude.
by combustible dust.
It's like corn cement.
As a result, Didion's master sanitation program did not require maintenance of areas at the facility that could present combustible dust hazards, but not food safety hazards, such as the dust collectors or their associated ductwork. Additionally, cleaning or periodic inspections in hidden overhead or limited access areas that could harbor combustible dust accumulations never occurred.
companies should ensure that the standards they are using are applicable and appropriate to the hazards inside the facility. Food safety standards are appropriate for preventing food hazards, such as pathogens and contaminants, from
Like if
reaching
you're,
consumers.
working in a
but they
meat
are not
factory, you're not just
intended
going to let
address
meat
workplace
juice
or process
stew all over the
hazards,
place,
such as
even if it's been
combustible dust. Appropriate
pasteurized.
tools,
It's gross.
such as dust hazard analyses, should be
Couldn't do anything
used
different
to
for
address
corn either.
process hazards like combustible dust.
A fourth safety issue at Didion is a lack of process safety leadership. In its investigation, the CSB found that Didion exhibited weak process safety
Nobody
leadership.
took responsibility for the
CSB
corn.
found that in the 5 years leading up to the incident, there were multiple smoldering fires and process upsets. Didion treated these conditions as normal, which caused employees to not recognize the significance of the smoldering fire on the day of the incident.
Yeah, every once in a while the corn catches fire, but that's just what happens out here in like the Midwest. You got the corn's got that Midwest attitude sometimes. So yeah, you just let it catch fire and just walk away from the smoke. It's not gonna spread. It's totally fine. It's not like the entire place is flammable. What's a little bit of fire in the corn? People like fire roasted corn. We'll sell that at a profit.
And the potential for it to transition to a catastrophic dust explosion.
Because of inadequate process safety leadership, Didion had a poor safety culture and weak safety programs. Although the facility clearly exhibited industry-recognized combustible dust hazards, Didion's leadership did not respond adequately, allowing an explosion that caused injuries and fatalities.
As a
So they
result,
knew
the
that
CSB
combustible dust could be a
recommended
hazard, but they're
that
just like,
Didion
we don't have
develop
to
and implement
give a shit
a
then.
process
Great, it's
safety
ignorance
leadership
again.
and culture program, and
Or
develop
not
a
ignorance, it's
comprehensive
negligence.
combustible dust process safety management system. Finally, a fifth safety issue that contributed to the incident at Didion is regulatory coverage of combustible dust. The Occupational Safety and Health Administration, or OSHA, outlines regulations for combustible dust hazard management for the grain industry in its
Yeah.
grain handling facility.
Did they not talk about
standard.
corn?
Didion was covered by OSHA's grain handling facility
Oh, they
standard.
are.
However, this standard does not incorporate safety management systems,
Oh.
such as incident investigations, management of change, and dust hazard analysis.
So basically, you are regulated by combustible dust standards. It's just that we're not giving you any guidance on how to do it right. You're just expected to figure it out.
And there are many other industries, such as food, agriculture, and polymers, that present the hazard of combustible dust, but are not subject to a comprehensive regulatory standard to address the hazard.
Since 2006, the CSB has called on OSHA to develop an overarching standard on combustible dust for general industry. But despite these repeated calls, OSHA has yet to act on the CSB's recommendations.
Therefore, in its report, the CSB once again recommended that OSHA promulgate a standard for all industries that handle combustible dust. The standard should, at a minimum,
Hey, that hazard to
require
get through
elements
OSHA
such
probably
as
in like
hazard recognition, dust hazard
2035
and
at
fugitive
best.
dust
It'll probably get voted down.
among
You know how
others.
OSHA is.
The
Can't get anything
CSB has
done.
been calling for a comprehensive standard on combustible dust for many years.
Yep.
Robust regulation is absolutely essential to keep tragic incidents like the
If
one at
only
Didion
government
from
agencies
happening
could
again.
pass regulations
But in
on
the
their
meantime,
own.
any facility that handles
Only we still
combustible
had
dust
that
should read our
Supreme Court
report and
precedent.
take action to
That'd be
apply the
great.
lessons learned at Didion. Doing so can prevent another deadly incident. Thank you for watching this CSB safety video.
All right. Let's see
For
who
more
the narrator,
information,
what the narrator's
please
name
visit
is.
csb.gov.
Everybody's so curious. Narration: Sheldon Smith. There's your name for you. It's not J.K. Simmons and it's not Morgan Freeman, but Sheldon Smith, a legend in the YouTube chemistry community and the, I guess, frankly, U.S. government communications community, if that's a community. Whew, wow, I made it. That was a long. This was a long reaction day. 2.5 hours of reacting to stuff, but hey, you know what? I got through all 4 videos in the thumbnail today, which I can't say I've done before. when I've had 4 videos in the thumbnail. So I'm proud of myself. I had a good time listening to 3 things that were all related to corn and corn syrup, and 1 thing related to dysprosium, and I hope you did too. I am probably going to just rest a little bit and then maybe hang out in the Discord later, which, hey, there's a Discord for this community in the description if you want to join the Discord and talk about science, and also Mega Man. We're there. Come join. I also have social medias if you want to follow me on the Twitters or the Blue Skies. I prefer Blue Sky just so I don't have to be on Twitter as much. And what else? Like the video, interact with it, hype it up, and tell your fucking corn farming brother out in Iowa that he should watch this video. And we'll be back next week with Mega Man Square Root minus infinity, or -1, Square Root of -1. Mega Man Square Root of -1. We'll be back next week with that on Monday, because I decided that would be a great breakup between MagMemel and MagMemel 1R. Because man, do I need to get around to Square Root minus infinity, -1 at some time. God damn it, I'm really tired. And then Tuesday we'll be back to Doom, more Plutonia experiment. It'll be cool. So thanks for sticking around. Thanks for watching some science with me. Thank you, VOD watchers, for watching science. I know VOD watchers are my goat when it comes to these science videos. Yeah, I will talk to everyone later. I'll talk to you when I see you. Have a good week or weekend. Until then, goodbye, good night. I'm gonna go and be a rambling mess elsewhere. See ya.